At 05:30 on the morning of July 16, 1945, the pre-dawn stillness of the New Mexico desert was shattered by the most momentous man-made explosion of all time. This was the fiery birth of the atomic bomb, culmination of centuries of step-by-step advance in the scientific quest, achievement of intense international effort by the Democratic Allies, product of unremitting research and toil since 1939. This instant of fury and flame and of violence beyond conception sounded the end of an age and heralded a new era in the destiny of mankind, a new relationship of man to his universe. Only a few carefully selected technical and military observers witnessed this test of new power that rocked the countryside at Alamogordo. The dramatic experiment took place just 6 days after provision of sufficient material for the first bomb. Development and construction of the bomb was the most closely guarded secret in scientific history. Solemn acknowledgement of success by two leading scientists foreshadowed the gravity of events to come. A world steeped in war did not know that a fearsome day was drawing near. On August 6th at 08:15 Japanese time, an Army Air Force B-29 dropped atomic bomb number 2 on Hiroshima, Japan's 7th largest city, a communications, military, and industrial center of considerable importance. A stunned universe now swiftly learned that man had a new weapon of shocking destructiveness, a weapon bordering on the absolute. In the blast, thousands died instantly. 70,000 persons were killed or listed as missing. 140,000 persons were injured. Of these, 43,000 were badly hurt. The city was unbelievably crushed. Of its 90,000 buildings, over 60,000 were demolished. The desolate remains were aptly described as vapor and ashes. Man had torn from nature one of her innermost secrets, and with his newfound knowledge had fashioned an instrument of annihilation. Menacing implications of this extraordinary weapon were frightening to everyday people.
Well, what did you think of that bomb we dropped on the Japs, Mrs. Glenn?
Oh, isn't it terrible? All those people killed.
3 days later, another B-29 dropped an improved bomb on the major Japanese seaport of Nagasaki, a highly congested, industrialized city boasting the best natural harbor in western Kyushu and extensive naval facilities. This bomb, exploding over the North Factory District, took the lives of 42,000 persons and injured 40,000 more. It destroyed 39% of all the buildings standing in Nagasaki before the calamity. The Japanese described their bleak, mutilated city as a graveyard with not a tombstone standing. These two terrifying blows were struck at Japan only after profound consideration of all the human and military factors involved. The atomic bombs were dropped to end the war quickly, and they did end the war quickly.
For 3 years, gathering momentum with each small victory, our forces had conducted an offensive against the war-bloated empire of the rising sun. Slowly, island by island, mile by mile, and then with ever-quickening sweeps, the combined land, sea, and air forces of the Allies drove against the borders of that empire, forcing it back until late in 1945, only the bastions of the Japanese home islands remained to be stormed. Our submarines were already roaming the Sea of Japan. Planes were devastating cities almost at will. The back of Japan's military might had been broken. Her navy was smashed and useless. Her marine transport was destroyed. Her industrial power was crushed. All this had been accomplished only with great sacrifices of killed and wounded among our personnel and tremendous cost of equipment and supplies. Ahead lay the greatest campaign of all, invasion of the Japanese homeland and close-in, desperate fighting. That this fanatical enemy would not quit until her last fighting man had been driven from his cave and killed had been established time and again by bitter experience. The price to be paid in casualties for successful invasion of Japan could not be estimated in exact dimensions. That the cost would be greater than in any other campaign of our long history could not be denied. This fact was accepted in its stark reality as plans to launch the invasion were completed. Ships in strong armadas, planes in great flotillas, men in vast numbers were already being gathered under a pre-Alamogordo strategy that had not been able to count on the aid of atomic weapons. Secretary of War Stimson, explaining the situation which existed when the atomic bomb became available for use against the enemy, designated employment of the bomb our least abhorrent choice. Weighed in the balance, he said, were the lives of thousands upon thousands of our fighting men. The total of United States military and naval forces engaged as potential combatants was 5 million men, plus millions more of our allies. The Japanese still had intact army forces of 5 million who would seek to repel the invasion. It was vitally necessary then to produce the greatest possible blow upon the Japanese people if the war were effectively to be shortened. Should the war follow a normal course, even with fortune favoring our efforts, military leaders estimated that it would be late in 1946 before the end of the war was in sight. 12 more months of war. The blow must be struck. It must be struck in a way that would leave the enemy no recourse, no choice, but quick surrender. A demonstration bomb on uninhabited Japanese territory was rejected by a responsible panel in that it would prove inconclusive, risk the security of the weapon, and fail to deliver its intended psychological blow. On July 26, 1945, the Japanese were solemnly warned of the penalties of continued resistance by the terms of the Potsdam Declaration, signed by President Truman and by Prime Minister Attlee of the United Kingdom, with the concurrence of Chiang Kai-shek, President of the National Government of China. Thus, the terms Japan later accepted were offered in advance of the atomic bombing. The Japanese rejected the Potsdam Declaration as unworthy of notice and fought on. President Truman made the final decision: the atomic bomb would be used.
At Hiroshima and Nagasaki, the atomic bombs destroyed the cities as entities. In panic, the populations of both cities fled. At Hiroshima, it was 30 hours before the first rescue teams were organized. What the bomb had produced was concentrated chaos, chaos from which no city of any nation could easily or rapidly recover. In these Japanese cities, no significant repair or reconstruction was accomplished until months later. The fabric of community life had been shredded in an instant. The Japanese proclaimed atomic bombs unendurable. 3 days after the second bomb was dropped, on August 12, 1945, the Japanese government surrendered unconditionally. Winston Churchill estimated that the lives of 1 million Americans and 250,000 British soldiers and sailors had been saved by this sudden shortening of the war. Statements of different aspects came from leaders who deplored employment of such a bomb. Solemnly aboard the Missouri, the Japanese signed the surrender documents. Advent of peace was signal for unrestrained rejoicing, but true and permanent peace was still to be accomplished, and atomic energy was a prime factor in the pattern of all negotiations.
What is the atomic bomb? What is this new and terrifying source of power which has intruded itself into the life and thoughts of each citizen? To the average individual, concept of nuclear fission was a remote component outside the orbit of his routine life. He regarded it as beyond the layman's comprehension. The bombing of the Japanese cities thrust it suddenly into his consciousness, made it real, made it a thing that would affect him and you and me and everyone, even in this generation. He did not quite understand it immediately. In the clutter of technical dissertations on the subject, in the press and from lecture platforms, he encountered conflicts and contradictions which confused him. Dire predictions by apparently reputable experts of such things as chain reactions which would disintegrate the Earth in one huge explosion left him with an uneasy feeling that man was tampering with the supernatural, that science had overplayed its hand. Gradually, with a sounder educational program and with time acting as an information filter, the basic elements of scientific progress in atomic research became more clear. With knowledge, panic began to disappear. It was replaced by certainty that man does now have access to new, annihilative or beneficent forces, forces summoning the wisdom and judgment of the ages in forging methods of control and in thwarting any application to evil ends. As a matter of fact, atomic science is not a new science, although the atomic age was thrust quite suddenly upon us, smashing the web of history, violently separating past from present. Yet in the explosion at Alamogordo, no great new principle of nature was either discovered or revealed. Although the atomic bomb was developed in the United States by an international group of allied scientists, impelled by the dread that Germany would develop such a weapon first, and although only one nation at present possesses an atomic bomb, no single nation can claim monopoly of atomic knowledge. Like most major technical developments, atomic science is the product of centuries of provisional conjecture and of experimental probing into the nature and structure of matter. All this started with the ancient philosophers and alchemists. Science began emerging into the light of historic days with Thales, the Ionian Greek, who described the power of attraction in electricity long before electricity as such was known. So-called father of the atom was Democritus, the Greek natural philosopher. Although he had no experimental evidence to support him, Democritus argued that all matter must consist of a number of fundamental pieces. He called these pieces atoms, thus bequeathing the word atom as a misnomer, for atomon, the Greek word, meant indivisible. 79 years before Christ, Lucretius, the Roman poet-philosopher, expounded atomic theory. After the downfall of Rome and throughout the Middle Ages, the atomic view of matter was nearly lost. Aristotelian philosophy, which implied a conflicting view, the continuity of matter, held sway during the long centuries. Then the 17th century brought the age of Galileo, regarded as the father of modern physics. The 18th century produced Isaac Newton with his physical laws. Man's conception of his universe was changing. There followed a procession of scrupulous observers of nature, endlessly asking of themselves and of others why and wherefore. Among them were John Dalton, the English chemist, with his atomic theory. Avogadro, the Italian chemist, who distinguished between the molecule and the atom. Berzelius, the Swedish analytical genius who undertook measurement of atomic weights. Michael Faraday of Irish extraction, the great exponent of experimental science. James Clerk Maxwell, Scottish physicist, stating that atoms were the foundation stones of the universe. Lord Kelvin, practical English genius, who systematized knowledge of mechanics, electricity, and heat in formulation of the laws of energy. Mendeleev, the Russian teacher, discoverer of the periodic system of the elements, who opened new vistas of atomic knowledge. Röntgen, German professor, whose discovery of X-rays provided for science a revolutionary tool. Becquerel, the French experimentalist, who discovered the phenomenon of radioactivity. Max Planck of Germany, who established the law of radiation, which led to the theory of quanta and modern understanding of the electronic structure of matter. Truly the parents of the future science of nuclear physics were the French team of Pierre and Marie Curie. From them came realization that the atom has a core or nucleus, quite different from the shell of the atom. it became apparent that the nucleus is governed by different laws of physics. Concentrating in the atomic field were great laboratories like the Cavendish Laboratory of Experimental Physics at Cambridge, England, fount of so much advanced knowledge in atomic science. Here worked Sir J.J. Thomson, who in 1897 discovered the electron, and his pupil, that giant of atomic exploration, Lord Rutherford, from whom first notions of the proton came, and who discovered and named the proton. He was the first to disintegrate the nucleus. He established the character of radium emissions and suggested what the true nature of the atom might be. Max von Laue of Germany interpreted the crystalline structure of matter, clue to the secrets of atomic structure. In 1905, Albert Einstein wrote the mass energy conversion equation. This was a great milestone, a great victory of man's genius. Einstein unlocked a treasure trove for experimenters. He provisioned them for vast new marches into the unknown. A student and co-worker of Lord Rutherford, Sir James Chadwick, in 1932, discovered the third fundamental particle of the atom, the neutron, an ideal projectile for splitting the nucleus. Final clue to the discovery of the neutron was supplied to Chadwick by Frederick Joliot and his wife, Irene Curie-Joliot, who had observed a peculiar property of the radiation emitted when beryllium is bombarded with alpha particles. Millikan measured the charge of the electron, and Anderson discovered the positive electron and the mesotron. Enrico Fermi, outstanding Italian physicist, in 1934 bombarded uranium with slow neutrons and created new elements. One of the best devices for producing new isotopes and new elements is the cyclotron, developed by Lawrence of the University of California. Niels Bohr, Danish physicist, is chiefly responsible for the planetary conception of the atom. First to probe the atom with X-rays was the young British physicist Moseley, who established atomic numbers of the elements through studies of their X-ray spectra. Deuterium, or heavy hydrogen, was discovered by Harold C. Urey and a group of associates. Rutherford called it one of the most important discoveries of the century. Heisenberg, collaborating with others in Germany and Denmark, elucidated the structure of complex atoms and announced the principle of indeterminacy of physical measurements. 1938 brought the startling discovery of fission of the uranium nucleus by neutron bombardment. Leading names in this research, carried on in Germany, were Dr. Otto Hahn and Dr. Fritz Strassmann. Lisa Meitner, working at Copenhagen, soon demonstrated that fission of the nucleus was accompanied by release of enormous amounts of energy. Allied scientists recognized that uranium fission was of far-reaching and practical importance, not only because of the tremendous release of energy with a single nuclear fission, but because of the possibility of self-sustaining chain reactions. Swiftly, scientists in the United States confirmed the German discovery. This was accomplished in January 1939. At this juncture, Allied interest in the military possibilities of atomic weapons began. Quietly, a military race was started. Free interchange of scientific information came abruptly to a halt. In the fall of 1939, Dr. Einstein wrote his now famous letter to President Roosevelt explaining the urgency of work on uranium fission. Roosevelt, a man of action, moved swiftly. An advisory committee on uranium was appointed. At the Bureau of Standards, the committee first met on October 21st, 1939. 8 recommendations were made to the President. Mentioned as possibilities were atomic power and an atomic bomb.
Time was short. Great Britain and France were already at war. The inevitable entry of the United States was accepted. Fear of German research stimulated activity in the United States and in England. One reason for the decision to concentrate forces against the Germans was recognition that German scientists could produce weapons of great devastation. The scientific competence of this foe was never doubted. Comparable peril from Japanese science did not exist. Early in the war, Allied intelligence had disclosed that Germany was increasing production of heavy water in the famous Norwegian hydroelectric plants at Ryukon and Vemork. These plants also produced vitally needed ammonia. The Nazi war regime was using heavy water for uranium research and also to improve the financial position of the Reich. Just before the invasion of Norway, the French government had purchased virtually the entire world stock of heavy water. At the time of the fall of France in June 1940, Joliot had sent 165 liters of the water to England. This heavy water, which twice had nearly fallen into German hands, permitted vital experiments to be conducted later at the Cavendish Laboratory, research which aided the Allies immeasurably. In the winter of 1942-43, with heavy loss of life, patriotic Norwegian saboteurs and British commandos wrecked equipment in the plants, and the Army Air Force did a neat job of strategic bombing which left the plants crippled. Meanwhile, a ferry carrying heavy water bound for Germany was sunk. German scientists made great strides in nuclear research, just as they had in aerodynamics and in rocket warfare. Their conception of an atomic bomb was an atomic pile guided out of control. They worked hard, but when the war ended, they still had not succeeded in creating a self-sustaining pile. They overlooked the use of a three-dimensional lattice and the role of fast neutrons in achieving detonation. They produced no plutonium. When Strasbourg fell, German atomic documents were recovered and a few physicists captured. Strategic circles then learned that vaunted German progress had lagged behind our own. News of the bomb drop at Hiroshima was a shocking surprise to intern German physicists. They had believed that construction of an atomic engine must precede a workable bomb, and that without German help, no bomb could be built. In June 1940, President Roosevelt organized the National Defense Research Committee. The Uranium Committee became a part of this group, reporting to Dr. Vannevar Bush. As Dean Pegram returned from a survey of British atomic research, Dr. Bush and the National Defense Research Committee determined on an all-out effort to develop an atomic bomb.
Chadwick and the other physicists agree entirely with us that given pure uranium-235, we can make a bomb that will work.
I'm going to see the president tomorrow. I'm sure that he will agree that the job has got to be done and that we'll get the support that we need.
Pearl Harbor had plunged the United States into war. An effective partnership of scientists, engineers, industrialists, and the military was formed. Work in universities and independent research laboratories was coordinated. Manhattan Engineer District, a new branch of the Army's Corps of Engineers, was established to administer work on military uses of uranium. Major General Leslie R. Groves was placed in charge of all activities of the project. The end of 1942 was a critical period. On December 2nd, the first self-sustaining chain-reacting pile was successfully operated at the University of Chicago. On that day, without fanfare, far from the field of battle, the atomic age loomed upon the threshold of history. This success galvanized authorization for construction of the great Clinton diffusion plant at Oak Ridge, Tennessee, and the giant plutonium-producing plant on the Columbia River at Hanford, Washington. Now the task assumed tremendous proportions in expenditure and effort. The expense was staggering, the obstacles gigantic, the possibility of failure ever present. Development of the atomic bomb eventually cost $2 billion. Scaled against the cost of total war, this figure loses magnitude. When the second bomb was dropped, the war had cost the United States $286,748,000,000. The daily cost of continuing the war was roughly $213 million. The plants at Hanford and Oak Ridge took form rapidly. The Oak Ridge pile started operating on November 4th, 1943. The first of 3 piles at Hanford began operation in September 1944. The Oak Ridge plants were designed to concentrate U-235 by different methods. U-235 is one of the 5 known isotopes of uranium. The Hanford plant was the source of that new man-made element, plutonium. Activity progressed at fever pitch. Problems, ugly, difficult, seemingly insuperable problems appeared. By dint of concerted effort, they were solved. As we look back now, what was accomplished appears as day-to-day miracles on a production line. At the time, it was work, 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 and more work. The first atomic bomb was assembled at Los Alamos, a secret laboratory in New Mexico. Scientific equipment was first obtained from universities and research projects. New equipment, built to specification, soon made Los Alamos the best-equipped physics laboratory in the world. When Dr. J.R. Oppenheimer arrived in March 1942 to take charge, he began to surround himself with a galaxy of outstanding scientific stars. The roster included many of the recognized leaders in modern-day physics and technical specialists from all parts of the world not then under enemy control. Sir James Chadwick headed an array of top British physicists at Los Alamos, and this group made invaluable contributions to technique and design. Professor J.D. Cockcroft, first to split the lithium atom in 1932, was another British consultant who gave vast help. Niels Bohr, one of the modern giants in physical science, made himself available after his escape from Denmark via Sweden. From Los Alamos came the bomb design and treatment of many theoretical problems. Measurements of the nuclear constants were refined and extended. Methods for purifying materials to be used were developed. Finally, in July 1945, a practical bomb was completed. This, briefly, is the history of the development of the atomic bomb. It was the harvest of science from many centuries, harnessed to the concentrated efforts of the greatest gathering of scientific brains ever assembled in one group with a single objective. When these men on July 16, 1945, exploded the first bomb in the Trinity test at Alamogordo, they were not releasing upon an unsuspecting world a weapon of unknown potentialities. The power of the bomb had been predicted within close limits by careful calculations, and while the explosion definitely was greater than the average expectation, it did remain within the calculated limits. Military weapons dependent upon nuclear energy were now and henceforth an inescapable reality. Energy released by explosion of one atomic bomb of the type used at Nagasaki is roughly equivalent to that generated by exploding 20,000 tons of TNT. 20,000 tons. 40 million pounds of TNT would fill 2 good-sized cargo ships. Yet, all this energy was contained in one bomb. Nor is this all. In the early stages, the explosion reaches a temperature unmatched except inside the stars. The light radiated from its surface can produce burns well beyond the dangerous range of blast alone. During the burst, there are radiations traveling at tremendous speeds and invisible to the eye that reach even those protected by tile and concrete walls or metal shields. These are gamma rays and neutrons that penetrate and kill with insidious efficiency. Danger persists after the blast has died away. Lethal materials, fission products, and the dregs of the bomb float about over the debris and beyond it. These exist in quantities equivalent in radiation to hundreds of tons of radium. Where they settle is death. These radium-like products give the atomic bomb its greatest deadliness. Under favorable conditions, they may last years or even centuries in dangerous amounts.
The cities of Hiroshima and Nagasaki were selected as targets after exhaustive study by military specialists, blast experts, and weather consultants. An air burst at about 1,800 feet was decided upon to minimize the lingering effects of radiation by dissipation of the bomb products in the atmosphere and to achieve maximum blast effect. Comprehensive studies by Japanese and by Allied scientists were made at the end of the war in both ruined cities. Damage from blast and from primary fires generated by the heat was unparalleled. Buildings collapsed, electrical systems were shorted, stoves overturned. A wave of secondary fires resulted, adding to the Holocaust. Flash burns from primary heat waves caused most of the casualties to inhabitants. Others were burned when their homes burst ablaze. Blast pressure and flying debris caused many injuries. Highly penetrating radiation from the nuclear explosion had a heavy casualty effect. A firestorm with winds of from 30 to 40 knots followed the blast at Hiroshima as air was drawn to the center of the burning area. Sheltering hills caused Nagasaki to be spared the secondary effect of a firestorm, although severe fires resulted from the blast. At first glance, damage at Hiroshima seemed more spectacular than that at Nagasaki, but comprehensive investigation told a different tale. Trees toppled at Hiroshima were uprooted. At Nagasaki, trees were violently snapped off at their bases. The radius of severe damage at Nagasaki was greater than at Hiroshima. Gamma radiation and neutrons caused thousands of cases of radiation sickness in Japan. First, the blood was affected, and then were impaired the blood-making organs, the bone marrow, the spleen, and the lymph nodes. Irradiation killed the young and immature lymphocytes. Germinal centers disappeared. The lymph glands decreased in size, leaving only walls and partitions. Blood would not coagulate and oozed through unbroken skin or seeped into many of the interior body cavities. Next, internal organs such as lungs, intestines, the liver or the kidneys were affected and their functions destroyed. When the irradiation was severe, organs became necrotic within a few days, marking the victim for certain death within a short interval. When the irradiation was moderate, many persons lingered from 2 to 6 weeks before the onset of death. Slight irradiation, when it did not cause death, often produced internal effects which lingered for months. Many persons who escaped both blast injury and burns were cut down from seemingly blooming health by the insidious radiation. Frequent symptoms of radiation sickness were exhaustion, then bleeding or high fever. As gamma rays took effect, rescuer often died before the person he had rescued. Surveys disclosed that severe radiation injury occurred to all exposed persons within a radius of 1 kilometer. Serious to moderate radiation injury occurred between 1 and 2 kilometers. Persons within 2 and 4 kilometers suffered slight radiation effects. When the war with Japan ended, a great mass of information about the atomic bomb had been gathered. But after the explosions at Alamogordo, Hiroshima, and Nagasaki, much scientific information was still incomplete. Lacking was significant information about blast efficiency, nuclear radiation, spectra, time developments, and thermal, magnetic, oceanographic, meteorological, seismic, and biological effects. There had been scant opportunity to obtain by careful measurement the multiple data required for complete statistics. Unavoidable lack of special instruments, lack of time, and loss of some instruments due to unpredictable factors had diminished results at Alamogordo. At Hiroshima and Nagasaki, too few measurements of radiation or pressure were made, and data on injury to personnel, while extensive, were far from complete. Physicians often did not know what type of injuries they were treating. The injured received little or no medical treatment, and trivial injuries often became serious. Methods of treatment were inadequately developed. Correlation of damage and injury data with pressure and radiation data was a subject on which more accurate information was essential. Physical effects of atomic explosion near or under water were entirely unknown. Information on all characteristics of atomic explosion was essential and could be obtained only under carefully controlled conditions. Medical reports needed amplification, especially with respect to the effects of radiation on personnel under varied conditions and the extent of radiation from bombs exploded under different circumstances. New bombing techniques had to be developed and new bombing tables worked out to meet the exacting requirements of this new weapon. The effects of atomic bombs on all types of military equipment demanded study. Beyond question, post-war research, design, and expenditures for national defense would be gravely affected. Only 2 atomic bombs had been used against the enemy. Both were aerial bursts in which the bomb was detonated above land targets. The effects of atomic bombs on ships in both aerial and underwater explosions must be explored to elicit and evaluate fundamental information. Application of information obtained to naval design, tactics, and strategy was essential to national security. Sea power has played a vital role in our destiny as a nation. It was important to know if and how the basic concepts of sea power were to be affected by weapons radically new. All this information was paramount in planning experimental work, in developing the effectiveness of the bomb, and in seeking to discover measures of defense. We could afford to be ignorant of no aspect of the bomb. In the light of this unsatisfactory situation, proposals were made to conduct controlled tests with atomic bombs to obtain all possible information. A program of large-scale controlled tests of other modern weapons had already been projected. The use of the atomic bomb as the implement to produce graded structural damage was expedient because it permitted the combination of damage analysis with studies of atomic effects. Individual proposals to conduct atomic bomb tests had come from General Arnold, commanding general of the Army Air Forces, and from Vice Admiral E.L. Cochran, Chief of the Bureau of Ships, and Vice Admiral G.F. Hussey, Jr., Chief of the Bureau of Ordnance. Leading legislators and Manhattan Engineer District agreed that full-scale tests must be undertaken. As early as 1944, it had been planned to use the atomic bomb against the Japanese fleet at Truk. But by the time the bomb had been developed, the base at Truk was no longer strategically important in the Pacific War. After the war, many proposals to use Japanese vessels as targets for atomic tests were advanced. Such proposals aimed at obtaining required information and at the same time eliminating Japanese naval power completely. It was soon obvious that tests against enemy vessels alone would not develop sufficient information. Basic differences in ship design and tactical policy between the United States and other navies rendered the use of some American vessels imperative. Because our attitude has been traditionally defensive rather than offensive, we needed to discover how United States ships would fare under atomic attack. We needed to re-examine the principle that ship design be matched to tactical function and similar tenets of naval doctrine. The shortcomings of comparative tests with miniature models and conventional explosives were equally obvious. Basic data must be derived from effects of the bomb on existing designs and structure. With such information at hand, model tests could then be continued and experimental work intelligently prosecuted. It was first necessary to formulate the so-called damage law for this new explosive with respect to ship targets and their orientation to blast.
On October 16, 1945, Fleet Admiral Ernest J. King proposed that the atomic tests be controlled by the Joint Chiefs of Staff. A committee headed by Major General LeMay of the Army Air Forces was directed to make studies and recommendations. Result of these staff studies was creation of Joint Task Force 1. With the approval of President Truman, Vice Admiral William H.P. Blandy, Deputy Chief of Naval Operations for Special Weapons, was designated commander of the task force. The Joint Chiefs of Staff approved the code name suggested by Admiral Blandy, and the venture was christened Operation Crossroads. Admiral Blandy was directed to organize a joint staff with adequate representation of the land, naval, and air forces, and with an integrated representation of civilian scientists. Major General William E. Kepner, one of the Army Air Force's top generals, became the Deputy Task Force Commander for Aviation. Rear Admiral William S. Parsons, who had been Associate Director of the Los Alamos Laboratory when the first atomic bombs were made, was named Deputy Task Force Commander for Technical Direction. He was the Enola Gay's weaponeer on the historic flight of that B-29 to Hiroshima. Rear Admiral T.A. Sahlberg, Director of Research and Standards in the Bureau of Ships and Deputy Member of the Tolman Committee for Applications of Nuclear Energy, became Director of Ship Material. Major General McAuliffe, who scorned demands of superior German forces for surrender of his embattled 101st Airborne Division at Bastogne, was appointed Ground Forces Advisor. Dr. Ralph A. Sawyer, now Dean of the Graduate School of the University of Michigan and veteran in the field of applied physics, became the top civilian scientist on the staff. Around this corps of men, Joint Task Force 1 was built. The Joint Task Force was charged with determining the effects of atomic explosives against naval vessels and equipment in order that strategic implications might be appraised. The directive further ordered that full advantage be taken of the opportunities to gain information on effects of atomic explosions on aircraft and on Army ground equipment, and that all possible data of scientific value be compiled. Secretary Forrestal authorized retention of 158 surplus United States naval vessels for the experiment. Meanwhile, Fleet Admiral Nimitz had saved important Japanese warships from routine destruction, and a choice of these vessels was offered the task force. The Prinz Eugen, modern German cruiser, was earmarked for the tests. The task force commander was directed to procure administrative and logistic support directly from the War and Navy departments, and on matters concerning the bombs to deal directly with Manhattan Engineer District. Assembly of the task force called for coordinated activity by many agencies of the government, notably the Army, Navy, Coast Guard, Marine Corps, State Department, Department of Interior, United States Public Health Service, Smithsonian Institution, Department of Commerce, and the Department of Agriculture. Personnel problems were critical. Highly skilled technicians were particularly hard to obtain. In spite of these facts, Joint Task Force 1 mushroomed into a highly integrated force of 42,000, with a staff that included more than 550 scientists and engineers. The experiments outlined were to comprise the greatest field tests ever undertaken. Because conduct of the tests would be governed by seasonal weather conditions in the South Pacific, a race against time began. The intricate operation was laid out in minute detail by the operations officer for Joint Task Force 1. A planning board met daily to integrate proposals from units scattered over the United States and the Pacific Theater. Even while the master plan was being prepared, preliminary activity was underway at 100 points on the globe, blending coordinated field groups into one great unit. One of the first problems was choice of a site for the tests. The basic requirement called for a protected anchorage 6 miles in diameter in an unpopulated region of the world, but less than 1,000 miles from a B-29 base. The site had to be free from violent storms, must have predictable winds directionally uniform, and predictable currents of great lateral and vertical dispersion. It must have a temperate climate. The site should be remote from fishing grounds, steamer lanes, and inhabited shores, and must be controlled by the United States. After much consideration, a little-known spot in the Marshall Islands was selected. Bikini Atoll, a dot on the map of the mid-Pacific, was destined to become a focal point for the eyes of the world. Situated 11 degrees, 31 minutes north, 165 degrees, 34 minutes east, Bikini met all requirements, except that its population of 167 persons had to be evacuated, and that its lagoon was inadequately charted. Commodore Wyatt visited the island and asked the natives to assist in preserving world peace by allowing their island to be used in the experiments. Even though this meant leaving their ancestral home, perhaps forever, the natives of Bikini were willing to do their share. Family heads selected Rongerik, an atoll 128 miles to the east, as first choice for a place of resettlement. Construction battalion units, with the help of 22 Bikini natives, began work at Rongerik. There were problems of delicate diplomacy in providing just the right number of new houses, just the right number of coconut trees, just the right number of water cisterns. These problems were soon amicably settled, and on March 7th, 1946, King Judah and his people were moved from Bikini and resettled at Rongerik. But the hearts of King Judah and his people are still at Bikini. They live in hope that one day they may return. Bikini Atoll consists of 26 individual islands spread out like beads in a necklace. When the task force was created, the only hydrographic charts available were of Japanese origin. These were inadequate. A new survey of the lagoon was ordered. The USS Bowditch and the USS Sumner, with several other vessels, undertook this survey. Standard sounding methods and the new acoustic bottom scanner were used. Wire drags located horses' heads, obstructions projecting from the coral bottom. While charting continued, troublesome coral heads were blasted from channel areas and potential anchorages. Others were removed to permit submerging of target submarines to desired depths. 40 Japanese mines were located and removed. Navigational markers, buoys, and beacons were placed to simplify movement in and out of the lagoon. The Fish and Wildlife Service of the Department of the Interior endorsed the site for the tests. Fish experts predicted no appreciable damage to fishery resources as a result of the explosions. Extensive tests were initiated to determine the effects of the bursts on marine life. A fish census, before and after, was made at Bikini to be compared with a control census taken at Rongerik. More than 20,000 fish were taken by hook, net, and seine for comparative study and analysis. Establishment of a system of supply was a major issue during these early days of the operation. To cope with this problem, Brigadier General David H. Blakelock, veteran of amphibious supply projects in the Pacific, was designated Assistant Chief of Staff for Logistics. General Blakelock was responsible for transporting, equipping, and feeding 42,000 men, and for installation of all ground facilities. Logistics for Crossroads was a tremendous task involving trains, airplanes, ships, records, fuel, construction and repair facilities, medical care, and the 1,001 jobs of servicing. Presidential delay of the tests added further complication, but eventually was contrived to afford better instrumentation. Aircraft were to play a key role in the tests. As the adaptability of aircraft for technical observation became clear, the relatively simple air plan originally proposed for the tests was expanded. The final concept of air participation utilized 150 airplanes with units from Army and Navy Air Forces. The primary air mission for Crossroads was twofold. First, to put one bomb over the target and to drop blast gauge and other recording instruments in the target area at the right time. Second, to record the effects of both blasts by instrumentation and aerial photography. An air operations plan which permitted flexibility and perfect synchronization was formulated. The lessons learned from projected practice missions were many. Compromises were made between tactical and scientific considerations. Training of air crews was initiated. At Roswell Army Airfield, New Mexico, an ideal location for practice bombing, a spirited competition began among specially trained B-29 crews for the privilege of dropping the Able Day bomb. This competition continued until shortly before Able Day. The desired bombing accuracy was within 500 feet of the bullseye, an accuracy 4 times better than required in normal combat action during World War II. Numerous devices were used to obtain great precision. These included simulated atomic bombs of correct weight, shape, and size. Among the early results were improved bombing tables and improved calculations for wind components. Photographic and instrumentation equipment was installed and tested. At Clovis, New Mexico, the Army Air Forces began tests to determine the modifications necessary to accomplish remote-controlled landings of B-17 drones, break to a full stop, a maneuver never before attempted. After an interval of training, radio-controlled takeoffs and landings of 4-engine planes were accomplished as seemingly routine procedure. Drones were flown above 25,000 feet to test the reliability of control equipment and of televising and telemetering equipment. New high-altitude electrical brushes were designed to improve television. Meanwhile, from carriers off the California coast and from air stations at Atlantic City, Brooklyn, and San Pedro, the Navy conducted training and experimentation with drone aircraft, particularly with catapult takeoffs of carrier-launched drones. During an air rehearsal on May 3rd, 1946, the first launching of a pilotless F-6F was accomplished from the deck of the Shangri-La. Control of the airplane during takeoff was exercised by a pilot sitting in a chair on the carrier deck. Extensive tests with Army B-17 drones and Navy F-6F drones developed standard operating procedures. New and advanced control techniques evolved. At the same time, 6 TBM pilots were trained for air control of 6 drone LCVPs, which were scheduled to recover water samples after each of the explosions for radiological study. Bomb-dropping rehearsals were held at the Albuquerque bombing range, and a full-scale dress rehearsal called Operation Zebra was carried out 100 miles at sea southwest of San Diego. During this operation, a simulated atomic bomb was dropped.
Between March 1st and June 5th, the air units of the task force began moving overseas for continued training. Each unit carried full complements of personnel and equipment. On Kwajalein, a small crescent-shaped island which boasted one of the finest bomber strips in the Pacific, was based Task Group 1.5, the Army Air Forces unit which operated the bombing aircraft. The group was under command of Brigadier General Roger M. Ramey of the 58th Bombardment Wing. At Eniwetok, the Army drone unit was separately based, and here intensive training in radio-controlled flights continued. Sea units, including the carrier Shangri-La, began extensive training operations in the Bikini area with drone landings at Ebi and Roy. A helicopter unit operated from the Sidor and Shangri-La and saw much service during the operations, particularly in the rescue of instruments from contaminated areas. Helicopters can hover, but without pontoons, they cannot float. This rotor plane was dunked on a practice mission. Salvage workers brought her up from the lagoon bottom to permit technicians to study the malfunction. The air movement between the United States and the Marshall Islands was tremendous. Day and night, planes flew the overseas air lanes. Their cargoes ranged from mice to men, from meat to mail. Alone, mail accounted for an average of 40,000 pounds a month. In all, 11,385 passengers and 3,280,000 pounds of freight were transported by air during the overseas period of Operation Crossroads. During the preliminary training period, the major part of the Joint Task Force personnel and equipment, including heavy shore installations, was being moved across the sea in ships. Among the data urgently desired from the atomic bomb tests was the reaction of Army equipment to such explosions, so that designs for new equipment would incorporate maximum resistance and so that new tactical doctrines and measures of passive defense might evolve. Sample equipment was gathered from the Signal Corps, Quartermaster Corps, Engineer Corps, Ordnance Department, Air Force, and Chemical Warfare Service. Coordinating these groups was the Director of Ship Material. Loading the principal equipment was mainly accomplished at West Coast ports. Careful deck layouts were made for exposure of the equipment, which was thoroughly lashed for the voyage and for the violence of atomic blast. Teams of specialists in damage assessment were organized under the Director of Ship Material to observe, record, and assess damage and to relate it to other types of damage after the tests. Test racks of Army and Navy materials were set up on target ships with weathering controls on non-target ships. The major objective of the entire experiment was analysis of the effects of atomic explosion on ships. Preparations to observe and record phenomena affecting ship structures and material were extensive and detailed. Perfection of methods and equipment for this purpose was an enormous task requiring skill, patience, imagination, and resourcefulness. Naval shipyards bustled with activity reminiscent of wartime. Alterations had to be made, new installations had to be completed, time schedules had to be met. Experts on boilers, turbines, pumps, Cranes, ship fittings, electrical equipment, paints, chemicals, lubricants, and fuels had a bewildering assortment of tasks to perform. First concern of the groups, controlled by the Director of Ship Material, was the flotilla of almost 90 target ships, plus reserve target ships. All had to be placed in proper material condition. From these vessels, items of historical importance had to be removed, and equipment which was extremely valuable or scarce had to be salvaged. Wiring circuits had to be set up and diesel generators installed to provide controls and power for equipment which was to be kept operating after the target ships were abandoned. Additional wiring circuits were required for delicate recording instruments. Mounting brackets had to be installed for hundreds of instruments, from pendulums to orientometers. Assembly of data was required on the structural strength and the watertight integrity of each target ship. Serious defects resulting from war damage on some of these ships were corrected. Loading plans were drawn up and followed in precise detail. New anchoring devices were designed. Since the effect of possible high waves on anchored ships was not known, it was planned to anchor each ship with a full scope of chain on one anchor and a short scope on a second anchor. To provide an added safety factor against failure of the first anchor chain, the second chain was hung in loops with fittings designed to fracture, paying out additional chain until the surge had diminished. These fittings were manufactured at Boston Naval Shipyard. Tests were conducted at Pearl Harbor to perfect the anchoring arrangements. 14 of the target destroyers had only one hawse pipe. Portable davits were fabricated and installed to accommodate the second anchor. 130 non-target ships had to be prepared for the many tasks assigned. Aboard some, electrical circuits for instruments were installed and tested. Other ships had to be converted to laboratories. Problems were encountered with the LSM-60 and with the bathysphere in which the Baker Day bomb was to be lowered. This pressure-proof bathysphere was built at Portsmouth Naval Shipyard, where submarines are usually built. The ship was equipped with a sturdy radio mast for multiple antennas. The Cumberland Sound was transformed into a laboratory control ship with elaborate radio equipment designed to arm and detonate the Baker Day bomb. The Albemarle was converted into the bomb-carrying and assembly vessel. The Burleson, headquarters for animal research, had to be transformed into a floating barnyard with feed pens, autopsy rooms, medical storage spaces, and laboratories. The hospital ship Haven was converted to house the radiological safety section. Instrument repair shops and laboratories were installed. 2 rafts of bridging were assembled on the beach at Bikini and towed to the target array for exposure to the explosions. Material was prepared for exposure in landing craft under conditions simulating an amphibious landing. Included was heavy ordnance material in storage condition. There was little rest for workers assigned to reconversion tasks. On target ships, work continued en route to Bikini and up to the final minutes before evacuation of the lagoon for the tests.
With all major units of the Joint Task Force at their overseas bases, final phases of training began in earnest, with installations and modifications of equipment being simultaneously accomplished. Final coordination of the tremendous organization had begun. To simulate the test-able bombing mission, a practice bombing range was constructed on Erik Island. A coral strip was cleared, approximating the top side dimensions of the primary target. 4 spotting towers were placed on the island for plotting the bomb drops by the transit method. These towers were manned by Los Alamos personnel. A radar detachment was established on Prayer Island, 1.5 miles east, for the purpose of tracking the bomb-carrying aircraft, communicating with the bombing commander, estimating bomb impacts, making weather reports, and obtaining high-altitude wind data. Training was intense, not only for the air crews practicing bomb drops over Erik Island, but for all other airmen, as they flew their assigned courses in the exact positions described by the air plan. Training was equally exacting for the many crews on ground stations and aboard ships, all essential cogs in the maneuvers. The Air Attack Unit carried out 23 missions in which practice bombs were dropped, and 6 dress rehearsals for a total of 29 major training operations in which simulated atomic bombs were dropped. The average circular error was 537 feet, a remarkable record. Practice bombing missions for Crossroads developed bombing techniques to a point that might not have been attained in several years of routine training. Bomb crews learned to make corrections for differences between winds at bombing altitude and those observed by the radar unit. At Bikini, it was noted that winds at lower altitudes were sometimes at right angles to winds at the prospective bombing altitude. Conventional methods for ballistic wind corrections did not permit compensation for such a cross-trail component. A method was found for estimating this deflection error and correcting for it. This proved one of the valuable results of the tests. Weather characteristics at Bikini resulted in a decision to move the orbit of the photoplanes into 12-mile slant range on Able Day, 3 miles closer than had originally been scheduled. Results bore out the wisdom of this decision. Photographs at the closer range showed better scale and improved definition. Because of the low elevation of Kwajalein, a ramp and a bomb loading pit were needed. Seabees erected a ramp capable of supporting a B-29. This led to the pit. When the bomber was in position over the pit, powerful hoisting equipment was used for loading. Air-sea rescue units were given elaborate training and coordinated with the operational flight plan. These seaplane groups operated a shuttle service between Ibai and Bikini and participated in reconnaissance. A second air-sea rescue unit was established at Kwajalein because of the possibility of takeoff accidents during the air activities there. Never before has a field experiment depended so much upon photography. No other event in history has been so extensively documented by means of the camera's eye. There were cameras everywhere, in the air, on the land, on the sea, and beneath the sea. Some in towers on the atoll were shielded by lead an inch thick. Others, such as these in the B-17 drones, were aimed by television as they dived into the atomic cloud. Virtually every type of camera available was used in one capacity or another. Relative importance was almost equally divided between still and motion pictures, each being used to complement the other in recording phenomena. While the photographic coverage of Crossroads constitutes a complete and detailed record of the operation and provides an invaluable historical document, the primary objective of the photographic units was to deliver film technically qualified to serve as a basis for scientific analysis. This called for precision and control in all phases of the operation, from maneuvering of aircraft to operation of photographic equipment. Photography provided the basic instrument for accurate measurements of movement as a function of time. This was required to analyze blast forces and other properties of the bursts. Cameras in fixed ground positions on the island offered relatively few problems in photographic control. In the air, camera platforms consisted of aircraft orbiting the target at fixed altitudes and given slant ranges, at ground speeds as high as 300 miles per hour. The exact position of each camera aircraft in space at time of detonation had to be recorded. The exact position of the bomber in space at the instant of bomb release, and the exact position of the target ships in relation to each other a few seconds before detonation had to be determined. These relative positions were determined by photogrammetric plotting and radar plotting, each using photography as a prime implement. An electronic control system was devised for starting cameras automatically. This employed a radio relay receiver in each photographic aircraft to pick up timing signals from the Cumberland Sound, and time delay relay controls to distribute the different starting impulses required by the various camera setups. For example, the relay control, operated by a signal at H-2 seconds, started a Fastex high-speed camera at -1.5 seconds, and also started an Eastman high-speed camera at -5/10 seconds. Remote control boxes started turret cameras and K-24 cameras. Sequence control equipment started 3 or 6 high-speed cameras in a sequence pattern. A time recorder was designed to provide an accurate time record of the operation of cameras. This consisted of a motion picture camera, which photographs 24 small indicator lights mounted on a panel around a precision clock. Ultra-high-speed motion picture cameras were operated at speeds as high as 2,000 frames per second. Some cameras had cylindrical lenses and moving strip films to record the intensity of the light from the explosions. Other cameras, moving great strips of film continuously, were called streak or blur cameras and interrupted light beam recorders. Moving drum spectrographic cameras were designed and built to get the wavelength distribution of light at all stages of the flash. 9 75-foot steel towers were erected on 3 islands of the atoll, Bikini, Nu, and Amen. These towers provided camera platforms on fixed axes and were equipped with electrical controls which could be triggered by gremlin timers. At other stations on Bikini and Nu were some extraordinary photographic devices. These included instruments that could separate events 1/10 of a millionth of a second apart. The rate of shock wave expansion was to be measured by long focus, high-speed cameras coupled with light beacons dispersed within the target array to determine the properties of the shock wave as a function of distance. The rate of development of the ball of fire and the unfolding of temperatures were to be recorded spectrographically. Light intensity was to be followed photometrically in 3 colors. The bomb burst was the nearest parallel to the atmosphere of a star that man could produce. Yet, these measuring instruments were within 5 miles of the radiating surface. Information of interest to astrophysicists would have evolved from these instruments. All this information was to be recorded within a few milliseconds, and there would be but one opportunity. It was a misfortune that this opportunity was lost through failure of the timing signals. The automatic control for triggering the equipment was rendered useless by a premature start, and the change to manual control was not made in time to record initial phases of the burst. 19 Army Air Force planes and 17 naval aircraft provided a camera umbrella for the tests unlike any the world had ever seen. 8 F-13s and 2 C-54s were modified for the job. Each F-13 carried 38 cameras, and each C-54 carried 32 cameras. The B-17 drones were also equipped with automatic cameras. Navy aircraft assigned to photographic work included F-6Fs, TBFs, and PBMs. Automatically triggered cameras were placed aboard many of the target vessels, and cameras aimed from observer ships augmented this battery. New optical instruments, glare-reducing icaroscopes, were used for the first time to photograph the early stages of the ball of fire. More than 1,500,000 feet of motion picture film were exposed during the operation, and the number of still pictures exceeded 1 million. Field laboratories were set up at the Army Air Base on Kwajalein and aboard the Sidor. Chief processing and assembly point was the Naval Photographic Center in Washington, where new techniques were used for filing of the material. Commercial laboratories were also used for processing color film.
To record necessary data during the tests, a great many new instruments were designed and manufactured, while thousands of standard instruments were brought into play. The manifold effects of the detonations required instruments to measure pressures and impulses, electromagnetic propagations, radioactivity, nuclear radiation, optical radiation, strains and stresses, winds, temperatures, waves, and many other local and remote phenomena. Elaborate sets of instruments were necessary to record seismological and oceanographic information. Pressures and impulses in the air and water, orientation of vessels with respect to 0 point, shock wave velocities, and the amount, quality, and time variations of light were also among the data to be determined. Many of the instruments were complicated and highly classified. Some were known only as black boxes. Others were such simple objects as pipes, cans, and oil drums. Still others were ball crusher gauges, aluminum foil rupture gauges, wire strain gauges, and piezoelectric gauges. Readings from many instruments were broadcast by radio and immediately telemetered. Some of the unusual measurements included changes in terrestrial magnetism, atmospheric pressure and conductivity, and ionospheric reflectivity. For remote measurements, field groups were situated at 34 widely spaced stations throughout the world. These outlying stations were to determine to what extent the occurrence of an atomic bomb explosion can be detected at great distance, a vitally important measure of defense. Detection methods included sensitive recording of radioactive content of the air, seismological measurements, and measurements of various radio anomalies. Choosing a target array best adapted for obtaining complete and accurate information was no small problem. Frequently, compromises in the choice of a target array had to be made by the various military units involved. No attempt was made to arrange the ships so that they would represent a fleet. This was not a test of air power against sea power. The array was not a tactical disposition. On the contrary, emphasis was on placement of vessels and equipment so that all graduations of damage would be obtained in direct relation to distance and orientation from 0 point. Such data would serve as a basis for predicting what would happen in a variety of tactical situations now and in the future. Mechanical damage was to be studied from the standpoint of ships as whole entities and of ships divided into their various parts, such as hulls, machinery, fuel tanks, magazines, and living quarters. Congress limited the number of United States combatant vessels to be used as targets to 33. In all, 88 hulls were exposed in Test Able, of which 28 were United States combatant ships. For reasons of economy, it was necessary to use ships considered inferior to those of modern design. Although in many respects, the ships used were not comparable to modern United States vessels constructed during the latter stages of World War II, these ships would provide adequate information to determine the character of damage. Since it was not known within close limits where the center of damage would be, it was necessary to disperse the ships and also the test items and instruments they carried. This, in the light of later events, proved wise indeed. Before the Able Day target array was finally selected, 19 different target arrays had been weighed and rejected. Later, more accurate and consistent figures on air blast properties became available. These supported the demand for denser grouping of the ships around the center, especially within 1,000 yards. Two British experts, Dr. W.G. Penny and Sir Geoffrey Taylor, suggested that the major combatant ships be placed in a sort of hexagonal arrangement around the point of aim. This would improve, they said, the range distribution under the random bombing dispersion expected. This suggestion was accepted and incorporated in substance. For Test Able, over a dozen moorings were used to array the central 9 ships in parallel lines. Each of these vessels was moored bow and stern and had a heading of approximately 0.85 degrees true. A typical mooring consisted of a buoy, a riser chain, a clump, 3 10-ton anchors, and 3 anchor chains. The clump was a 9 or 10-ton concrete block resting on the bottom of the lagoon. It was attached to 3 or 4 anchors by 500-foot chains. The riser chain connecting the clump and the buoy was made as short as feasible to limit the swing of the vessels. The Able Day target array listed 5 battleships, including the war-damaged Nagato, once pride of the Japanese fleet. Modern German construction was represented by the cruiser Prinz Eugen, which, though trim appearing, had been bombed and repaired many times and was not completely watertight. The Nevada, the New York, the Pennsylvania, and the Arkansas were the 4 United States battleships used. While not of modern design, they possessed great resistance to battle damage. They had very heavy hull protection, torpedo protection systems, and heavy side and deck armor. There were approximately 600 watertight compartments in each of these ships. In a modern battleship of the Iowa class, there are approximately 900 such compartments and a very heavy armor deck and upper side plating of treated steel for protection against bombs and fragments. One famous ship in the array was more modern in her subdivision. This was the aircraft carrier Saratoga, originally designed as a battle cruiser and converted into one of the first Navy carriers. She had approximately 1,000 watertight compartments, 22 main bulkheads, and 2 longitudinal bulkheads through 70% of her length. Her underwater arrangement was similar to that of modern battleships and large carriers. An inner bottom above the bottom shell was fitted between the innermost torpedo bulkheads for about 80% of her length. Among the modern vessels used were the Independence, a carrier of the cruiser hull type, and several heavy-hulled submarines capable of withstanding great hydrostatic pressure when submerged. Submarines were considered among the best gauges for both tests, particularly for the underwater test. In addition to the 5 battleships, 4 cruisers, and 2 aircraft carriers, which comprised the principal ships of the Able Day target array, there were 12 destroyers of varying types, 8 submarines, 19 transport vessels, 5 modern landing ships, 30 smaller landing craft, and 3 concrete dry docks and barges. In the final plan, the intended 0 point, occupied by the flame-colored Nevada, was situated 5,400 yards from Bikini Beach. Shallow water and coral heads prevented use of a closer location. The Nevada was chosen as the central battleship because she was one of the most rugged ships available. The 4 other battleships were placed at 300, 600, 1,100, and 1,200 yards from the 0 point. The Sakawa and the Salt Lake City were placed broadside to 0 point at 600 yards. The Prinz Eugen was bow on at 1,800 yards. The Independence was spotted at 300 yards. The Saratoga was placed about 1,800 yards from 0 point, where it was anticipated she would not be damaged so greatly that she could not be used, if necessary, as the principal target ship in Test Baker. The heavy-hulled Skate was moved close in to 250 yards. 1 light-hulled and 1 heavy-hulled submarine were placed at 800 yards, a similar pair at 1,600 yards, and a third pair at 2,200 yards. An additional heavy-hulled submarine was placed at 1,500 yards. All the submarines were surfaced, so they would be exposed to the full force of the explosion. 8 of the 12 target destroyers were deployed in 2 lines on opposite sides of the 0 point, one line extending from 900 to 2,800 yards, and the other from 1,750 to 2,100 yards. 3 of the remaining destroyers were placed at 300, 500, and 750 yards, while the 4th was a full 2 miles from 0 point. The 19 attack transports were in 2 principal curved lines, one line extending from 600 to 3,200 yards, and the other from 800 to 3,700 yards. The ships of one line were almost broadside to 0 point, and the ships of the other line presented their bows to 0 point. 4 LSTs were placed in a line extending from 1,500 to 4,000 yards from 0 point, while 6 LCTs formed another group from 500 yards to 4,000 yards, stretching out toward Bikini Island. 4 LCIs were in a line beginning at 1,800 yards and extending to 4,000 yards from 0 point. 2 patrol bombers and another LCT were on the outskirts of the array. Along Bikini Beach, at approximately 200-yard intervals, were 4 LCTs, 5 LCMs, and 6 LCBPs, 1 LST, and 2 LCILs. 1,000 yards from 0 point was a floating dry dock. A concrete oil barge was stationed at 300 yards and another at 1,200 yards from target center. Whenever possible, the ships were disposed in curved lines so that one vessel would not shield another. In the spiderweb target array for Test Able, 24 ships were located within a 1,000-yard radius from the intended 0 point. In a fleet formation at sea, it is probable that only one capital ship would be found within this radius. In a fleet anchorage, 2 to 4 ships would normally be found. In a crowded harbor with ships alongside docks or moored, a dozen or more might be in such close proximity.
Arranging the ships in the exact location specified by the operations plan was hampered by a lack of good navigational markers. Photographic surveys disclosed the errors, and ships were moved to conform strictly to the requirements. For analysis of technical data, it was necessary to determine with a fine degree of precision both the position and the orientation of each target vessel with respect to the point of detonation. Here again, major reliance had to be placed on photographs made seconds before the blast. Long focus cameras on island towers were to chronicle these minute details. One vital area was the mock stem region, where direct pressure from the exploding bomb and pressure reflected from the water surface would be so close as to coalesce into a single cylindrical wave. Here were disposed most of the instruments to measure duration of the positive pulse, peak pressure, and shock wave velocity. Advances made during the war in television were put into practice during Operation Crossroads. Elaborate installations were made on bikini for television cameras to scan the explosions at close range and transmit the pageant of events to the scrutiny of observers and to image recording devices. Television aided, too, in aiming the drone aircraft, which were sent with split-second timing into the Able Day atomic cloud and over the cauliflower of the underwater burst. The communications and electronic plan for the operation contained a total of 203 different channels involving 348 frequencies, which ranged from 300 kilocycles to 30,000 megacycles. A constant workload fell upon electronic instruments. With the rear areas, liaison had to be maintained despite all difficulty. In the forward areas, communication and electronic problems were multiplied many-fold. Electronic science was called upon to provide systems for observing and measuring technical effects from remote locations, to operate drone planes and boats and the telemetering devices which they carried, to furnish navigational aids for aircraft, to operate various triggering devices for starting cameras and instruments, to provide television coverage of the explosions and their associated phenomena, to determine the effects of the blast clouds on electromagnetic propagation, to carry descriptions by newsmen and broadcasters to a waiting world, to deliver with utmost speed more than 400 high-quality radio photos to newspapers and magazines at home. Besides these projects, the electronics program included determination of the effects of atomic explosions upon standard electronic apparatus. Radio propagation difficulties between Kwajalein and Bikini complicated communications problems. On the Mount McKinley, flagship of the task force, as many as 6 radio, teletype, and broadcast carriers were on the air simultaneously. The proximity of transmitting and receiving antennas produced acute interference problems. Added to these troubles were sunspot and skip distance effects. Radio teletype, a new factor aboard ships and aircraft, was used extensively. For the first time, news stories were filed by radio teletype from a plane in flight. Press wordage alone, transmitted in 5 languages by radio teletype, exceeded 2.5 million words during the operation. The very high-frequency network functioned as easily as a dial telephone system, although plagued at intervals by interference and propagation troubles. Need for scrambler systems was soon established, particularly during voice discussions of highly classified topics. Communication studies were made and frequency shifts arranged. Exact tuning of transmitters alleviated but did not eliminate many interference problems. Volume of traffic was enormous. While the overall success was gratifying, completely satisfactory voice and teletype communications were never obtained
on a day-to-day, 24-hour basis. Much of the communication traffic was with the Rear Echelon Organization, commanded by Rear Admiral Frank J. Lowry. During the absence of field units, the Rear Echelon had a multitude of tasks to perform in order to preserve a high degree of coordination. On Baker Day, electronic silence was strictly observed, lest stray signals interfere with the detonation of the bomb. Weather was a vital issue in both tests. Good weather, with a maximum of 3/10 cloud coverage and favorable winds, was obligatory. This placed heavy responsibilities on forecasters. 5 months before the Able Day drop, the Air Weather Service began to gather data on weather conditions in the Bikini area. They soon had many answers, particularly on upper wind structures. One type of wind, designated the east-west type, was characterized by east winds at the surface and west winds aloft above 10,000 feet. Another wind, designated the easterly type, was characterized by easterly winds up to 60,000 feet or more. It was decided that the easterly type was required for the Able Day drop, since the mushroom cloud would move westward with the wind and across open sea. Ships, aircraft, and shore-based units could thus be disposed to the windward sectors and many dangers of radioactive precipitation averted. Since required conditions would obtain only 1 day in 4, meticulous care had to be exercised in setting a suitable day. Through use of upper air wind data, diagrams were made to appraise the rate and direction of cloud movement. These data were needed to judge how far away any serious radioactive effects might be encountered. Accurate predictions, as much as 48 hours in advance, were essential because of the complexity of the task of evacuating the lagoon. New techniques for tropical forecasting were worked out. Pertinent charts, diagrams, and forecast tables were developed. Experience was gained in using radar to obtain upper wind measurements. Upper air soundings were made daily by radiosonde balloons and by high-altitude aircraft. The mobility of weather aircraft permitted rapid assembly of weather reports equal to the output of a dense network of weather stations. In addition, they provided more detailed reports of cloud conditions than would be possible from surface stations. Aerial weather reporting was augmented by ships in the area. Added was a great mass of information from the regular network of weather stations. A staff aerological unit was set up aboard the Mount McKinley, assessing weather data on a 24-hour continuous basis. Because of its importance to the success of these costly experiments, weather information was handled on the communication circuits with operational priority. Research for Crossroads demonstrated the need for an extensive network of upper air forecast stations and for complete upper air maps to high levels. Yet, so accurately were conditions predicted during the training period that operations were canceled only once because of unexpected weather. To the task force commander, safeguarding personnel was of surpassing importance. Admiral Blandy directed that every possible precaution be taken and that safety rules imposed by the medical staff be given unquestioned heed. With so many of the task force personnel exposed to dangerous conditions, the fine record of safety bears witness to the performance of the medical division. Safety advisor for the task force was Captain George M. Lyon. He was responsible for the safety plan and for the instruction of all members of the task force. Colonel Stafford L. Warren, who had been chief of the medical section of the Manhattan Engineer District, was the head of the group denoted the Radiological Safety Section. Much was known in advance about the unique hazards associated with atomic explosion. Guarding personnel against these dangers was of vast importance. The Radiological Safety Section was responsible for all measurements of radioactivity. These were required to evaluate potentialities of the explosions in causing casualties aboard target vessels, some of the most significant information sought in the experiments. These efforts meant not only prediction of intensities of all nuclear radiations, including alpha, beta, and gamma activities and neutron flux, but also the measurement of radioactivity in the air, in the water, in materials, in target and operational vessels, and near instruments and experimental animals. The group was further charged with measuring the radiation exposure of all personnel involved in the operation. In accordance with accepted safety standards, the daily limit of human exposure to gamma radiation was set at 1/10 Roentgen.
Under Captain R.H. Drager, the Naval Medical Research Section, which embraced a further complement of Army personnel and civilians, was responsible for exposing experimental animals, determining the kind and the extent of injuries, and investigating methods of diagnosis and treatment, principally of radiation illness. Hazards other than radioactivity, which damage control teams and other boarding personnel might encounter, were evaluated by the Damage Control Section. Such hazards included oil-covered decks, falling objects, distorted ladders, weakened tanks, noxious gases, flooded compartments, fires, escaping steam, electrical shocks, corrosive acids, contaminated drinking water, and secondary explosions. Not all information of benefit could be derived from instruments alone. Physiological, hematological, and pathological information was to be obtained for the study of the radiation illness, the major hazard of atomic warfare. To obtain this information at Bikini, many persons volunteered to expose themselves at vantage points of great jeopardy. Naturally, their offers were rejected. Injuries incurred by animals would provide abundant clues to effects upon men exposed to atomic explosion. Important, therefore, was the choice of animals for the experiments. Goats, pigs, and rats were selected. These species provided a range of sensitivity to ionizing radiations, and all were hardy enough to withstand tropical conditions. For specialized studies, a few mice and guinea pigs were added. Goats were chosen because their relative radiosensitivity is roughly comparable to man's. Included were 4 goats having previously established conditioned reflexes. Rats were chosen because they are less radiosensitive than man. A few guinea pigs were included for comparative purposes, since guinea pigs are more radiosensitive than man. The mice selected came from special strains, some with high predilection and some with low predilection to cancer. Seeds and grain insects were used to study the genetic effects of radiation upon plant and insect life. Besides animals, the Naval Medical Research Section was responsible for exposing a wide variety of biologic materials: seeds, hormones, vitamins, sera, bacteria, medical and dental supplies, and samples of military clothing. Resulting changes were to be correlated with observed physical data such as air pressure and radiation intensity. Collaborating in this work were the Army Chemical Corps, the Army Medical Corps, the Army Veterinary Corps, the U.S. Department of Agriculture, the U.S. Geological Survey, and the Naval Medical Research Institute. Headquarters for most of these studies was the floating laboratory, the Burleson, which was equipped for work in pathology, hematology, radiobiology, and biochemistry. Sailors with farming experience were assigned to the many tasks of animal husbandry. The animals were to be distributed on 22 target ships for the air explosion and on 4 target ships for the underwater explosion. Some were to be tethered. Some were to be placed in compartments above and below decks. Several goats were partly sheared, and anti-flash burn cream was applied to the depilated skin. Changes in the blood count are the most sensitive index to irradiation effects. Blood counts were made in the hematology laboratory of the Burleson on all animals before exposure to radiation and afterwards at frequent intervals. Some animals were to be supplied with filtered air to reduce their exposure to fission products. Instruments were placed close by the animals to record physical data for correlation with the injuries received. In this way, interpretation of the factors producing injury could be rendered. These data included intensity and duration of thermal radiation, air pressure, wind velocity, deck and bulkhead accelerations, and gamma ray and neutron intensities. Instruments brought into play were temperature recorders, ultraviolet recorders, gamma ray recorders, air pressure gauges, ionization chambers, Geiger counters, and Sony cameras for recording on film intensity and duration of the gamma ray radiation. Air purification equipment of the Army Chemical Corps was made available for testing. Collective protectors were used to filter air for certain groups of rats. Detailed records were kept of each animal. Periodic blood counts and all evidence of radiation effects were carefully recorded. The pedigrees and characteristics of many animals were already known. Particularly was this true of 120 white mice supplied by the National Cancer Institute. Simulated agents of biological warfare, sealed in aluminum cases, were provided by the Army Chemical Corps for study of mutations and other radiation effects. Effects of the bombs on soil fertility was another topic of interest, particularly to the Department of Agriculture. Caribou loam from Maine, Decatur clay loam from Georgia, and Houston black clay from Texas were exposed. Despite the excellent record in radiological safety, there were deaths from other reasons. One man was drowned. 2 deaths resulted from aircraft accidents. 1 man was accidentally electrocuted, and 1 man died of methyl alcohol poisoning. Security control throughout the operation was painstaking. Top secret details of the bomb had to be closely guarded, and extraordinary precautions were necessary because of the presence of so many observers. One of the primary security tasks involved screening of hundreds of scientists, technicians, and specialists. Detailed investigations were made of persons who would have access to highly classified equipment, laboratories, or reports. Photo review panels were set up for the release to news agencies of still and motion pictures. Photographs made in the forward areas were developed in controlled laboratories. Each photograph was subject to classification. Credentials were examined to admit authorized persons only to restricted areas. Marine guards were assigned as sentries at the bomb assembly areas at Kwajalein, and Marines also guarded vital instrumentation areas at Bikini, Amen, and NU. The Joint Chiefs of Staff, after consulting the State Department, had determined that foreign observers would be invited to witness the tests, even though the operation was secret. The positions of these observers and their access to information were controlled. Each nation, with membership in the United Nations Atomic Energy Commission, was permitted to send 2 official observers and 1 newspaperman. In all, 34 official foreign observers witnessed both tests, plus 10 representatives of the foreign press. Many of the foreign observers were outstanding scientists. Others were ordnance or technical military experts. The observers were based aboard the Blue Ridge and the Panamint. Both the Secretary of the Navy and Admiral Blandy addressed them before the tests, emphasizing that the tests were not a warlike demonstration, but serious and earnest experiments to obtain all possible information about atomic explosions in an unbiased scientific manner. Operation Crossroads focused attention of the world upon Bikini. At this distant spot were assembled many of the world's outstanding newspaper correspondents and scientific writers, still photographers, radio reporters, newsreel cameramen, and television representatives. No attempt was made to censor news copy. Thousands of news stories described the different phases of the operation in the world press. Radio photos sent from Bikini and Kwajalein established new speed records for long distance and high fidelity transmission. They were widely published. 615 commercial radio broadcasts were made from the ships of the task force, primarily from the Mount McKinley and the Appalachian. In this way, the world was made acquainted with the objectives of the tests and with their planning and execution. By the time the date was set for an all-out task force dress rehearsal, designated Queen Day, the Air Arm had achieved split-second timing and precision. Meanwhile, the spirited competition to decide which bomber crew would drop the bomb had come to an end. The privilege was won by the crew of Dave's Dream, led by Major Woodrow P. Swancutt. His bombardier was Major Harold H. Wood. Modifications to prepare Dave's Dream for the bomb were made by technicians assigned by Manhattan Engineer District. To ensure maximum precision, a Norden bomb sight was altered. The normal intersecting crosshairs were replaced by adjacent, parallel crosshairs, which allowed the bombardier to keep the aiming point image between them. The thickness of the hairs in a normal sight represents a trajectory variation of 400 feet in a drop from a 30,000-foot altitude. The bombs chosen for both the Able and Baker explosions were designed and built at the Los Alamos laboratory. Both were of the type used at Nagasaki, the most powerful available for the experiments. For the air explosion, a detonation altitude of about 500 feet was chosen. Preparation of the bomb was directed by Rear Admiral Parsons, who commanded the bomb and instrumentation group aboard the Albemarle. The laboratory unit of this group delivered the first bomb to the crew of the plane a minimum period before takeoff. 2 weaponeers were assigned to ride the plane and arm the bomb after the aircraft was a safe distance from Kwajalein.
The Queen Day dress rehearsal was an operational success. At last, all was ready for Able Day, tentatively set by Admiral Blandy as July 1st, 1946. Throughout months of tedious preparation and preliminary tests and public discussion, tension had increased. As Able Day drew near, the eyes of the world swung toward the atoll in the Marshall Islands. The atomic bomb was topic of the day. It was on the lips of housewives, school children, and the man on the street. The cue which would set the great test organization in motion now must come from the weatherman. Aerologists watched a high-pressure area north of Midway Island, a low-pressure area in the Philippines, and a wedge of high pressure above Bikini. It was check and double check, judgment weighed against judgment, probability balanced against possibility. On June 30, the forecast came. Good bombing weather. The mission was definitely underway. According to plan, signal flags were hoisted. Promptly, evacuation of the target vessels began. Shipboard rituals of orderly departure took on new meaning. After a round of salutes to captain and quarterdeck, the colors of each ship were struck. 90 support ships must move out of the lagoon in the allotted time. Slow-moving craft were the first to leave. Larger ships lumbered after them. Before dawn on Kwajalein, the command aircraft thundered down the runway, her engines shattering the tense silence of what had seemed an endless night. As watches told 0423, it was airborne. Aboard was Brigadier General T.S. Power, the air commander who would direct the air operation from his post aloft. Fast evacuation craft dashed through the target array, embarking the last-minute sentinels. Some of these men had made final adjustments on recording instruments. Others had battened down hatches and sealed the ships. When all details were completed, yoke flags were hoisted on the halyards. Dave's dream was on the loading ramp, the bomb safely loaded, the crew ready and waiting. From Admiral Blandy at 0542 came the final go-ahead. 3 minutes later, the bomber taxied down the ramp toward takeoff position. Kwajalein had become alive. The roar of many engines contributed to the clamor. It was as if the envelope of night had given way to an envelope of sound, darkness giving way to dim. Dave's dream is roaring down the runway, engines singing. She is airborne at 0555. Now, each minute counts. 8 minutes after the bomber takeoff, evacuation of the lagoon has been completed. Silence settles over Bikini Lagoon. The last ships are standing out to the open sea, heading for their stations. Among them is the Mount McKinley, nerve center of the Joint Task Force. Attention swings to the air phase of the operation. This is a tactical action involving 85 aircraft in a tight geometric formation. The air pattern contrived above the target array has as its center the vertical projection of the aiming point carried to an altitude of 30,000 feet. Around this presumed perpendicular, at given slant ranges and altitudes, and in fixed orbits, circle drones and drone control planes, photographic aircraft, radiological reconnaissance aircraft, pressure gauge dropping planes, radiometry, precipitron sampling, and oceanography aircraft, air-sea rescue units, and orientation and command aircraft. Positions in the complicated flight pattern must be accurately controlled and recorded by radar and photography. Control of air movements during and after the tests must also be guided by many other factors, particularly those of radiological safety. By 0800, General Kepner is able to report that all aircraft are airborne and that the bomber is over the target array preparing for its first dry run. Aloft, visibility is good. The dry run is successful, and at 0849, Admiral Blandy signals for the start of the bombing run. Dave's dream is at 29,000 feet. True airspeed is 299 miles per hour. The bombardier makes corrections for wind and bomb weight, and a small compensation for the inherent tendency of this type of bomb to hit short. Bomb bay doors are open. The timing signal sounds. Only seconds left to go. On the cry, bomb away, the world's 4th atomic bomb plummets earthward. As the bomb bay doors snap shut, the bomber executes her 150-degree turn to the left. The closest photographic aircraft is the F-13, which from a position 1,000 feet to the right of Dave's dream takes motion pictures of the bombing run and photographs descent of the bomb. Instantly upon bomb release, 2 B-29s drop blast pressure recording instruments into the area above the target. This equipment settles into position over the array. Falling for slightly more than 48 seconds, about 500 feet above the surface of the lagoon, the bomb explodes. Unfolded are a myriad of majestic, startling, and awesome effects, a panoply that only the cameras can record in faithful detail. The most important events of atomic explosion occur during the first fraction of a second after detonation. Nuclear reaction is completed within a few millionths of a second. Then comes a brilliant flash of bluish light that overwhelms the vision of even distant observers and blanks out photographic lenses. In these heavily filtered, high-speed photographs, the flash is subdued to a glowing orb. The motion has been frozen for better discernment of the progression of events and for study of the early phenomena. This ball of fire, less than 1/100th of a second old, has a diameter of about 180 yards and is expanding at the rate of 10,000 feet per second. Before this stage is reached, gamma rays and neutrons have already escaped to produce their lethal effects. Energy equivalent to 20,000 tons of TNT now resides in this incandescent sphere as heat and pressure. Losing brilliance rapidly, it is still almost as bright as the sun. Its internal temperature, fed by nuclear energy, is reckoned in millions of degrees. Its pressure is almost a ton per square inch. At 2/100ths of a second, the ball of fire has flared to a 250-yard diameter. Less rapid is its expansion now, and a shock wave, outracing the fireball and carrying nearly half the total energy of the explosion, rushes out at 6,000 feet per second to batter the target ships. Hitting the water, the blast wave produces a reflection that rejoins the original shock, multiplying the pressures and increasing the damage. When the wave strikes the water, it produces a white circle of spray. The expansion rate of this circle provides the best method of measurement of shock wave properties. For almost a full second, excessive pressure prevails around the fireball. Then this pressure gives way to partial vacuum. Intense heat evaporates inflammable material and explosive mixtures are ignited. Flames belch against the sides of the vessels. Fires break out. Sudden rarefaction cools the surrounding atmosphere until no longer can it carry the water vapor associated with high humidity over the tropic sea. A dense cloud forms into a beautiful white hemisphere, enveloping the blazing ball of fire. At this juncture, damage from the intense heat and light radiation ceases. This supersaturation effect diminishes the number and the violence of fires as compared to atomic explosion over dry regions. High winds associated with the shock wave snuff out many of the fires which the intense heat already has created and smite ship superstructures a staggering blow. As the cloud chamber begins to dissipate, 5 seconds after detonation, a ring cloud forms, soon to be evaporated. Within this emerging fireball, there yet remains a great store of energy. Turbulent and still glowing, it shoots up with an initial velocity of 150 feet per second, carrying off all but a fraction of the deadly fission products. As incandescence disappears, the mushroom cloud develops. With powerful up-thrusting surges which seem to regenerate themselves again and again, the mushroom cloud becomes a boiling mass of energy, filled with toxic gases, conflicting winds, twisting flames, and superheated air currents. The cloud assumed its characteristic shape 20 seconds after detonation. The lengthening stem and the bulbous head give it the appearance of a gigantic flower trying to span the distance between Earth and sky. Less conspicuous because of its transient nature is the froth of base cloud, soon to be sucked up into the stalk of the mushroom. At 18,000 feet, approximately 2 minutes after detonation, a thin, wraith-like cap of ice crystals has formed, quickly swallowed by the rising cloud. Within 150 seconds, the cloud has reared its majestic pillar up to 5 miles, roughly the height from which the bomb had been dropped. By 400 seconds, it has risen to 7 miles. Eventually, it reached 40,000 feet, but by this time, shearing upper winds have been whipping it to shreds. Drifting in the winds, the cloud stratified and lost its shape. Within an hour, observers at Bikini could see it no more. For many hours, reconnaissance aircraft tracked its wind-borne wandering. Later, from remote points, came reports that traces of increased radioactivity had been detected. On the way to the target array, 9 minutes before detonation, one F-6F drone developed an inoperable aileron at 28,000 feet, spiraled out of control and crashed. With this exception, the flight plan of the drone fighters was carried out with notable success. Landing at Roy, the Navy drones brought back a wide variety of scientific data and samples. Equally notable was the success of the drone bombers of the Army Air Forces. Every drone aircraft was recovered on completion of its mission and safely landed at Eniwetok. This was a remarkable record, as a high rate of loss had been expected in the remote-controlled flying operation. Instead, there was not a single abort for engine failure or other mechanical reasons. Primary mission of the drones was to gather air samples in dust-collecting bags and in air and oil filters, and to carry both television cameras and recording instruments into areas too dangerous for operation of manned aircraft. All drones also served as airborne targets to determine the effects of atomic blast upon aircraft. Its automatic cameras grinding out a photographic record, one B-17 drone was flown directly into the center of the radioactive cloud at 24,000 feet, approximately 7.5 minutes after detonation. 3 other B-17 drones were maneuvered around the outskirts of the cloud at 13,000, 18,000, and 30,000 feet. 3 drone fighters completed their transits into the cloud at 10,000, 15,000, and 20,000 feet. The drone which entered the cloud at 20,000 feet had a slight nose-up position upon entry and emerged at 26,000 feet, evidently caught in strong updrafts within the cloud. Temporarily astray, this drone was not recaptured by its control plane until 43 minutes later. It was then over Wotho. The radio compass aboard one B-17 drone proved its value when, remotely keyed, it turned the bomber toward Eniwetok while the distant control plane was attempting to overtake it. Because of its reserve fuel load, a critical factor at 30,000 feet in affecting relative speeds, the mother aircraft did not overtake the drone for 15 minutes. At Eniwetok, residual radioactivity was measured. Some of the aircraft were designated hot, their air samples indicating they had flown through areas of severe radioactivity. Airbags had been opened by AGSTOT relays when the planes were visually inside the cloud or when Geiger counters indicated they were in dense radioactive areas. The bags were closed by the radio relays 15 seconds later. Air filters allowed air to flow freely through filter paper, forming deposits of radioactive material. Oil filters also were used to collect deposit samples of the cloud. The strongest samples of radioactivity were obtained from aircraft which had flown through the cloud at higher altitudes. All drones carried flight analyzers which recorded normal accelerations, air speeds, pressures, and altitudes as functions of time. Because they were distant from the epicenter at detonation, the drones did not experience any marked acceleration from the shock wave. Air currents did produce mild accelerations of the drones at the threshold of the cloud pillar and within it. As far as engine performance is concerned, it was established that aircraft can operate close to atomic explosion. The drones carried a great variety of electronic equipment for testing. Results of electronic investigations were generally negative. So little electronic or mechanical interference or malfunction was recorded that it may be strongly assumed that radio-controlled drones or electronically controlled rocket missiles can be used successfully in areas close to an atomic explosion. Radioactivity had little effect on transmissions. A strange effect was produced upon the iconoscope of the television camera in the nose of the B-17 drone which entered the center of the cloud. The light intensity of the detonation was so great that a miniature image of the early blast was burned permanently on the screen. The iconoscope is being preserved at Wright Field. No radar reflections were obtained from the blast cloud in Test Able. Attenuation of signals which passed through the cloud was observed, the phenomena lasting as long as 7 seconds at the higher radar frequencies. A few minutes after detonation, the B-GOR, jointly controlling the drone boats with the aid of aircraft, approached the lagoon for visual control. At the same time, 4 TBM planes were launched by the Sidor with conning officers and radiological safety monitors aboard. 44 minutes after detonation, the first drone boat, an LCVP, its stern trailing a cloud of smoke to identify it to the control planes, started toward the target array to collect water samples. Another followed a short interval later. Within 4 hours of detonation, these radio-controlled boats had collected a number of water samples which were immediately flown to Kwajalein for analysis. Other aircraft were performing important functions. A PBM, equipped with special radiometry instruments to photograph and measure the heat radiation of the blast, orbited the target array at 9,500 feet and 15 miles slant range. This equipment produced particularly valuable scientific data. Radiological reconnaissance aircraft and photographic aircraft continued their flights for a long period after detonation, being replaced periodically by relief aircraft. These crews acquired a steady flow of the data necessary to maintain an uninterrupted record. 3 seaplanes carried equipment for photographing and measuring water waves resulting from the burst. The crew of one of these planes also actuated by radio the synchronized tower cameras on the islands. Close inspection of the damage wrought by the Able Day bomb awaited completion of safety precautions. Through binoculars, the distant watchers had seen a number of fires break out. They had strained to identify the ships involved. As the blast wave passed over the ships, observers had noted a black cloud above each vessel. Scientists believed that these clouds consisted of soot and dirt shaken loose by the blast and forced out of the stacks and boilers of the ships. Salvage units awaited the signal for re-entrance to the lagoon. These units were equipped with safety helmets, rescue breathing apparatus, mine appliances, and other instruments designed to detect and measure noxious and explosive gases. 5 hours after detonation, after careful radiological survey by the safety groups, the word came from Admiral Blandy, re-enter. As units steamed into the lagoon, full import of the tremendous effect of the atomic bomb became immediately apparent. Spread over the oil-splotched lagoon, observers saw a vast array of smoking, soot-smudged vessels as if the remnants of a great naval conflict. Naturally, eyes first turned toward the Nevada. She was still afloat, but now her bright color was dimmed by a heavy coating of soot. That the bomb had missed the intended 0 point was soon obvious. Instrument measurements later showed that it had burst 710 yards short and to the left of the Nevada's foremast. This error was far greater than had been thought probable, nearly 4 times greater than the average error maintained in practice bombings. Exhaustive analysis of available photographs and other data has been made, but this analysis has not accounted for the error. A major bombing error was not completely unexpected. The target array and instrumentation were so devised that the location of the burst did not nullify the results of the test as far as graded damage was concerned. Protective margins allowed in positioning the ships and in distributing the instruments achieved recording of graded damage despite the magnitude of the error. The miss did prevent optimum functioning of many instruments. A line of sonobuoys designed to telemeter wave height was rendered useless. The projected 0 point was closest to the Gilliam, an APA. The Gilliam was one of the principal instrument-bearing target ships, and her loss had not been anticipated. She had been only 65 yards from the spot directly beneath the explosion. Within 1 minute after detonation, she sank. So badly ruptured, crumpled, and twisted was she that divers later found her barely recognizable as a ship. 4 other ships were mortally damaged and sank before re-entry or a short time later. These were the Carlisle, another APA, 430 yards from 0 point, the destroyer Anderson, 600 yards, the destroyer Lamson, 760 yards, and the new Japanese light cruiser, the Sakawa, which had been 420 yards from the center of the explosion. Heavily damaged and torn along the center line at the stern, which had faced 0 point, the Sakawa remained afloat for 25 hours before she sank. Of the 5 ships sunk, all had been within 760 yards of the center of detonation. The most conspicuous wreck still afloat was the USS Independence. Only the stamina which naval engineers had built into her as the first of the cruiser hull carriers allowed her to survive. Only 560 yards from blast center, she experienced a succession of serious fires and low-order explosions which rapidly developed aboard her. In heavy seas, she would have suffered progressive flooding from lack of water tightness above the waterline. Her military efficiency was virtually non-existent. Her bulkheads were buckled. Her hangar deck was a jumbled heap of rubble and ruin. Her warped flight deck was gashed and rent and had a crazy tilt. Both elevator platforms had been blown overboard by pressure trapped between decks. Nevertheless, her engines and boilers were relatively undamaged, and guided by tugs, she moved under her own power to a position for Test Baker. Even closer to the detonation, at 400 yards, was the submarine Skate. Demolished was her light superstructure, but interior damage was not sufficient to prevent her from getting underway. Yet her efficiency as a combat ship had been seriously impaired. Her radio and radar antennas were gone. Both her periscopes were inoperable. Her pressure hull proved how rugged are all ships of this submersible type. This inner strength hull was not substantially damaged, and no flooding resulted. She had been closer to the burst than 4 of the ships sunk. The stern of the Nevada was 615 yards from 0 point. Her superstructure was distorted. Her fire control antennas were beyond possible use. A portion of her main deck was dished in. Side casing panels on all of her boilers had been blown out. She needed steam to operate her power plant, her steering gear, and other equipment. This meant that it would be 24 hours or more before she could get underway at the slowest of speeds, even if a combat crew were aboard to perform the multiple tasks of repair. In an instant, her military efficiency had been destroyed. The Pensacola, 700 yards from point of detonation, would have required a voyage to port for extensive repairs before she would again be a fighting unit. Instruments revealed that she had been subjected to blast corresponding to a wind velocity of 384 knots. She had lost water tightness above the second deck, and her longitudinal structural strength had been slightly impaired. Her stacks were ruined, and her topside hatches had failed. Casings had been damaged in all 8 of her boilers. 3 additional ships had been immobilized, principally because of damage to boilers, superstructures, and stacks. These were the Arkansas, 620 yards, the Salt Lake City, 895 yards, and the Hughes, 920 yards from 0 point. Not immobilized, but suffering serious loss of military efficiency were the concrete YO-160 at 520 yards, the Crittenden, an APA, 595 yards, the ARDC-13 at 810 yards, the Dawson, an APA, 850 yards, the destroyer Rhine, 1,012 yards, the destroyer Talbot, 1,165 yards, the LST-52, 1,530 yards, and the Saratoga, 2,265 yards from 0 point, seemingly unscathed except for minor secondary fires. Yet the Saratoga's vital plane elevator had been jammed by the hammer-like blast from above. This indicated extreme vulnerability of elevators on old carriers to such form of attack. 9 other ships suffered moderate loss of military efficiency. They were the Nagato, 790 yards, the Brule, 990 yards, the YOG-83, 1,035 yards, the Banner, 1,190 yards, the Prinz Eugen, 1,195 yards, the Barrow, 1,340 yards, the New York, 1,545 yards, the Pennsylvania, 1,550 yards, and the Butte, 1,990 yards. In summary, every ship within a half-mile of 0 point had either been sunk or had suffered serious loss of military efficiency. Military efficiency of ships as far as 1,500 yards was impaired. One thing was clear: no pinpointing was necessary for a bomb of this type to wreak major damage. Naval experts studying the crippled ships readily saw that here lay a serious challenge to modification and redesign. It was to exposed surfaces and superstructures that the high-velocity air blast wrought its worst havoc, with destroyers proving the most vulnerable. Orientation to blast had important effects. Blast, reflected or focused into passageways and structural pockets, scored heavy damage. Reduction of damage from both blast and flash heat by even light shielding afforded an interesting study. In most cases of radar antenna damage, impairment was so great that repair work could not be accomplished at sea. Boiler damage meant reduced speed and impaired operation of ordnance and machinery. Significantly, the boilers of the modern carrier Independence were undamaged at 560 yards, although all 4 of her stacks were demolished. In general, modern boilers with double casings withstood the blast. Boiler vulnerability proved to be related to stack height and construction. Modern stacks of welded construction fared much better than older riveted stacks. Old boilers of American design proved extremely vulnerable to atomic blast. All of the old United States battleships suffered serious damage to boiler casings and brickwork. Strangely, the Nagato's boilers were unscathed. Damage to the Pensacola involved not only major boiler damage, but incipient failure of main hull structure, as evidenced by damage to main strength column supports in the engine room and the fire room. Her sister ship, the Salt Lake City, also had major boiler damage. The newer Prinz Eugen's boilers at 1,195 yards were undamaged, and the main visible damage was to superstructure. Even when stacks were damaged without accompanying boiler damage, the boilers could not be operated until repairs had been made or emergency stacks built. This meant immediate crippling of ships through loss of power. Extent of damage from blast down the stacks of a ship under full steam can only be contemplated. Electronic equipment was seriously damaged up to 1,200 yards and slightly damaged up to 2,500 yards. Principally, major damage was to wire radio antennas, bedspring-type antennas, and radar reflectors of light-gauge metal. Vacuum tubes and other delicate components remained generally undamaged by blast effects wherever they were securely shock-mounted. Metal tubes fared better than glass. Small, compact electronic equipment fared better than large equipment in resistance to the blast. Shock mounting, shielding, and streamlining proved their value. Within a radius of 900 yards of detonation, electrical equipment and instruments exposed topside suffered severe damage. In general, damage to electrical equipment was not one of the chief factors contributing to loss of military efficiency. Ordnance equipment on exposed vessels suffered little severe damage, although fire control systems were seriously affected by the loss of radar antennas. Optical systems stood up well. Modern rangefinders, normally rugged and shockproof, withstood the explosion with no internal damage. Range keepers, too, suffered light damage only. All exposed ammunition, as well as that in magazines, withstood the heat and blast virtually without change. Torpedoes, mines, and depth charges were not detonated. 12 torpedo warheads on the Independence, while not exploding, were consumed by the fires aboard and gave the flames new impetus. It was possible there was an ammunition or pyrotechnic explosion aboard the destroyer Anderson before she rolled over and sank. Packaged ammunition exposed for special testing remained undamaged at distances greater than 1,000 yards. Pyrotechnics in thin cases but otherwise unshielded were unaffected beyond 1,000 yards. Wrapped propelling charges and mortar powder increments in plastic cases, however, were damaged at distances up to 2,100 yards. Fuel and ammunition loadings for Able Day had been the subject of much discussion when the target array was planned. No fuel or ammunition fires occurred as the result of the burst. Fuel and ammunition loads varied from 15% to full. To prevent spreading of fires and loss of valuable instruments and experimental animals, vessels in the upwind sector carried the lighter loadings. Extending to the outer margins of the array, 27 fires had broken out aboard target ships at intervals after detonation. These fires were in exposed locations. All were extinguished by salvage crews except that aboard the Independence, which burned itself out. Many fires within 1,500 yards of zero point were snuffed out by winds associated with shock wave. Others smoldered for long intervals before bursting into active flame. Burlap wrappings of Army quartermaster material was a frequent source of fire. Jute and manila cordage burned readily. Induced heating from metal parts surrounded by combustibles caused scorching or fires. Scorch marks were found on combustible material on virtually every ship. Color, gloss, and reflectivity were definitely related to the inflammability of such material. Strikingly, fires were of much less importance in overall damage than they had been at Hiroshima and Nagasaki. Humidity differences, the presence of the cloud chamber effect, and the fact that ships are fundamentally fireproof were contributing factors. Fires in the sterns of the Sakawa and the Independence did create serious damage to these vessels, but not many other fires gained comparable headway. Salvage crews extinguished many blazes, but there were fires still burning when the sun went down on Able Day. No oil fires started in the water, although such fires had been feared. Seepage of oil did not commence until passage of the blast wave. Army tanks and heavy guns and mobile equipment suffered no impairment of operational efficiency beyond 600 yards. Unarmored vehicles, searchlights, and aircraft structures were damaged severely at ranges up to 1,200 yards, with minor damage as far out as 2,500 yards. Plastics were susceptible to the heat flash, which caused warping, fusing, and bubbling. Disintegration of laminations occurred where plastic bonding material had been used. Exploration was made of the degree of affinity of concrete for radioactivity and of resistance of concrete to blast. Baked paint in thin single layers on Army equipment withstood the heat of the blast much better than multiple layers of flat paint on decks and bulkheads. Ranges of scorching and blistering were irregular. Thermal screening by steam or fog undoubtedly contributed to this irregularity. Baled and packaged clothing was damaged by fire several miles from zero point. Food packaged in metal or glass containers exposed at 500 yards was cleared for consumption 4 days after Able Day. Heavy rubber behaved well. Pneumatic tires and electrical cables were virtually undamaged beyond 600 yards. Thin rubber coatings and objects of sponge rubber were often badly charred. Experimental animals and their varied reaction to atomic explosion were objects of immediate study. Approximately 90% of the test animals were recovered alive. Some had been killed by indirect blast effects or lost in ship sinkings. In many cases, hair of the animals came out in patches. Male animals showed hemorrhage into the reproductive glands. One misfortune which resulted from the large bombing error was that no animals were in sheltered areas within 650 yards range. For this reason, no data on the effects of intense neutron radiation were obtained. Various experiments were attempted to preserve the lives of animals. Some animals lived for a long time. This increased survival may have been the result of treatment or due to the great biological variation in survival which occurs among all animals. The most successful treatments were penicillin injections and multiple blood transfusions. Blood counts were taken and tables of comparative figures compiled. Of pigs exposed within a 1,000-yard radius, 50% had died by August 1946. In the same radius, 85% of goats and 75% of rats exposed were dead. Differences in animal mortality were partly due to differences in shielding provided the different groups. 15% of pigs and rats outside the mile radius were dead by August. Only 5% of goats in this area on the fringes of the target array were dead. Pathological studies of organs of animals killed by the blast or victims of radiation were carried out with painstaking detail. Color transparencies were made at various stages to preserve medical data. Hemorrhages, ulcers, inflammatory reactions, and other injuries gave graphic evidence of the serious consequences of irradiation illness. Hearts, brains, lungs, livers, kidneys, stomachs, and intestines all showed irradiation effects. It was from such pathological examinations that the fatal results of acute radiation illness were demonstrated. For about 1 month, mortalities from radiation injuries continued to mount. Evidence indicated that thermal radiation would produce serious burns on exposed personnel up to about 1,700 yards. Exact distances would vary markedly with atmospheric conditions such as the presence of dust or humidity. At lesser distances, slight shielding would protect against burns, but death might result from ionizing radiation. A few animals within the lethal radiation zone were protected by shielding and survived. While an exposed person at about 1,200 yards would probably die, a well-protected person might be as close as 600 yards and still not receive a fatal dose. Experiments show that the gamma radiation is reduced 50% by 1.25 inches of steel. 9 inches of steel would reduce intensity to but 1%. Neutron radiation within 650 yards is an even more deadly killer, and light steel shielding affords little protection. At these close ranges, however, the general blast effects are so tremendous that neutron and gamma radiation, deadly as they are, become superfluous lethal factors. Animals exposed to atomic explosion became hyper-irritable, showed loss of appetite, muscular weakness, diarrhea, and increased rate of respiration. The direct injuries caused by air blast alone were hemorrhages in the lungs and in the bowels, the air-containing portions of the body. Following Able Day, the animals were intensively studied. The data obtained has helped to clarify the knowledge of atomic bomb injuries. The import of what medical men learned is of great significance. More than 50% of the animals situated within a half-mile of 0 point had already died or were soon to die. Between 15 and 30% of the animals exposed at distances from a half-mile to a mile from detonation perished. A small percentage of the animals outside the radius of 1 mile also died. As days went by, the death toll mounted. From the animal studies, important conclusions could be drawn. At close range, death to exposed personnel would be instantaneous and due to multiple causes. The air blast wave and thermal radiation would be most effective against exposed personnel up to 1,000 yards. But at even greater distances, the thermal radiation would produce loss of military efficiency through burns to exposed skin, and the air blast wave would produce indirect injuries, such as those caused by flying missiles or impact against bulkheads or stationary objects. The chief cause of death outside the 600-yard radius would be ionizing radiation. Gamma radiation would produce serious injury at great distances, even in personnel protected from blast by a thin layer of steel. By the end of November 1946, over 1,666 of the 3,619 animals exposed to the blast were still alive, roughly 43%. If they had not been killed for study, 351 more animals would also have survived. Generally, there was no persistent radioactivity after the test, and examination of the ships by various groups was not seriously delayed.
From an operational standpoint, Test Able was considered very successful. Graded damage had been produced to meet requirements. Instrumentation had been good, and a mass of important data had been accumulated. A basis had been established for determining the vulnerability of ships and men. Conclusions could be substantiated with abundant evidence. The effectiveness of the bomb was now more specifically known. It had become a measurable quantity. No longer was it a mythical agent of supernatural power. In the summary of the Able Day damage alone, impressive though this damage appeared to be, it was apparent that the full significance of the test could not be manifested. Amid the sober reflections, there was an occasional humorous note, and crews of surviving ships were not above advertising the hardihood of their vessels in the face of atomic blast. While the press of the world was hashing over results of Able Day, Joint Task Force 1 began preparations for Baker Day, a test of atomic explosion under the sea. Much remained to be done. There had been 4 air explosions. This was to be the first detonation beneath the surface. Damaged ships had to be photographed, cleared of debris, and repaired. New instruments set out and difficult diving operations completed. The target fleet had to be redisposed. Extensive preparation was required for handling and detonating the bomb underwater. Instrumentation for this test would be less handicapped, since the point of detonation was accurately fixed. The Baker Day bomb was to be lowered from a landing ship, the LSM-60. This vessel had been modified to provide radio transmitting and receiving apparatus, a laboratory for bomb assembly, and rigging apparatus to lower the watertight caisson in which the bomb was to be enclosed. This bathysphere was fitted with a coaxial cable for transmission of ultra-high frequency signals. Sensitive relays aboard the LSM would be closed by tone-modulated signals. These signals, in turn, would close heavier relays, controlling the power supply to the arming and firing circuits of the bomb. To avoid error, a repeat-back system was installed. The relays, upon being closed, operated oscillators which provided the repeat-back signals. These signals modulated a high-frequency transmitter, which sent signals to operate lights on a registering panel aboard the Cumberland Sound. An additional repeat-back circuit was used to verify closing the arming voltage circuit of the bomb. In rearranging the target array for Test Baker, it was known from the results of the Able Day burst that few ships within 500 yards of the bomb could survive. The Saratoga and Arkansas were placed within this range and broadside to 0 point, but their size precluded mooring other major ships close by. Submarines were to play an equally important part in the second test. Submerged, they were to gauge the effects of underwater blast on modern hull design. In all, 88 hulls were exposed. The general spiderweb plan was again used, with the LSM-60 as the central ship. In the allocation of the 5 battleships, the nearest was the Arkansas, placed just 200 yards from the caisson. The other battleships were at 800, 1,000, 1,100, and 1,200 yards from 0 point. Because of predictions of what would happen in the underwater blast, Admiral Blandy decided to moor the Saratoga 500 yards from 0 point to prevent her from sinking too rapidly after the blast. This was done to permit photographic analysis of the behavior of her flight deck under severe hull pressure and tremendous wave action. Slack moorings, however, allowed her to drift when the wind changed on the morning of the blast. She was but 350 yards from 0 point at detonation. The battered Independence was moored at 1,200 yards. Two cruisers were exposed end on, one at 700 yards and the other at 1,200 yards. The Prinz Eugen was at 1,970 yards. 8 destroyers were placed along a curved line at distances from 850 to 3,500 yards. 3 other destroyers broadside to the explosion were at 700, 1,250, and 1,750 yards. The submarine pilot fish of heavy hull design was placed 260 yards from the blast. 2 pairs of submarines, one light-hulled and one heavy-hulled per pair, were placed at 800 yards and 1,300 yards. 2 more heavy-hulled submarines were placed broadside to the blast, one at 750 yards and the other at 1,200 yards. And a light-hulled submarine was placed broadside at 1,800 yards. 6 of these submarines were submerged just before the test. A floating concrete dry dock was placed at 1,200 yards, and 2 concrete barges were moored at 800 and 1,000 yards. 17 APAs extended in 2 curved lines from 0 point. One line end on from 500 to 3,700 yards, and the other broadside from 700 to 3,200 yards. 33 landing craft were used. 4 LSTs extended in a single line from 1,700 to 4,100 yards. One had a floating bridge tied astern. 1 LST was end on at 750 yards. Another was placed on Bikini Beach. A line of 5 LCTs and a line of 4 LCIs were arranged at distances of 2,000 to 4,000 yards from 0 point. 4 LCTs, 5 LCMs, 6 LCVPs, and 2 LCILs were also zoned along the beach at intervals of 100 yards to simulate an amphibious force making an invasion. Oceanography was more significant in the underwater test. Studies of currents in the lagoon had been used to predict the spread of radioactive areas following detonation. Ocean water normally flows into the lagoon continuously over the eastern and northern reefs. Outflow occurs principally through NU Channel. Dominant features of water movement inside the lagoon are a wind-driven surface current flowing in a west-southwest direction and a return current at the bottom. Water transfer is very slow. It normally requires 25 days to exchange 1/2 of the lagoon water with ocean water. Velocities of currents at different depths were determined, and the direction in which the currents veered was recorded. The average drift of the upper 15 feet of water over periods from 8 to 36 hours was determined by current poles. Frequent observations were taken. At night, radar reflectors were invaluable. Dye markers were used primarily in channels and over reefs where other methods were not practical. Variations of temperature and salinity were studied. These studies clarified certain obscure results of current measurement by normal methods. Data collected enabled scientists to determine the path of contamination in the lagoon and the rate at which the lagoon would be flushed. This information was important in planning details of the operation relating to the safety of personnel, methods of approach to target ships, and placement of vital instruments. Thus, it was known in advance that by the end of Baker Day +1, the strip of contaminated water would reach Bikini. Accordingly, since access to the land areas would later be denied, plans were laid for the early rescue of instruments by helicopters and by landing parties.
July 25th had been set as the tentative date for Baker Day. Once more, attention was focused on weather. Long-range forecasts were good. Preparations for the test went ahead with all possible speed. Then came a threat of upset. An equatorial front moved northward toward Bikini. Thunderstorms and showers developed. By the day before Baker Day, it was still raining. Faces were glum. Tasks still to be done were made more difficult by the downpour. But Crossroads' famed luck was holding up. The front swerved to the northeast. Drier air invaded Bikini. Good weather would prevail. Cloud cover would be at a minimum. Surface winds would be only 7 knots. Visibility would be excellent. Baker Day was set, July 25th, 1946. Evacuation of target ship personnel began immediately. A general exodus commenced as the Sidor steamed out of the lagoon. Last-minute submerging of the unmanned submarines began. Crews had spent many long hours of preparation for this work. After the pilot fish had been submerged, her radar mast popped above the surface because of a shifting of exterior ballast. It was now too late to reballast. Similar difficulties were encountered with the Sea Raven. Her bow and her periscope shears were showing, but after much work and the loss of one suspension anchor, total submergence was achieved. At 0524, the Mount McKinley began to move out of the lagoon, now presumably clear of all personnel. But a last sweep with binoculars revealed emergency bunting flying from the yardarms of the Gasconade, a target APA. Aboard her were a group of last-minute personnel who, through oversight, had not been evacuated. Their signals were espied, and they were hastily removed to safety by the conserver. The lagoon was clear by 0620. Aircraft were already aloft as air components moved into position. Reports were streaming back from weather reconnaissance planes, which were making far-flung weather sweeps north and east of the lagoon. 2 command aircraft were on station at dawn. At 1-minute intervals, 7 F-13 photographic aircraft soared into the morning sky, followed by 2 C-54 photo planes. F-13 altitude for the Baker mission was 15,000 feet. The overall flight plan was similar to that on Able Day, except that the photographic orbits had been moved into 7 miles slant range as against 12 miles on Able Day. One F-13 was assigned to a course which would bring it directly over the target at 30,000 feet to make vertical photographs at the moment of detonation. 1 C-54 and 2 B-29s carried press and radio reporters and news photographers. A PBM bore aloft the President's evaluation board. Another PBM carried the radiological safety and technical observers who were to report early results. Army and Navy drones and reconnaissance aircraft soar into position. As Howe Hour approaches, 32 Army aircraft and 29 Navy aircraft are weaving through the air pattern. Mapping planes are making their last-minute runs over the target area. Scanning summaries of the air operation, General Kepner reports ready to the task force commander. Watches are consulted. Radio silence is imposed upon the task force. The bomb is being armed by radio control from the Cumberland Sound. Eyes turn toward the LSM-60. 90 feet below her and halfway to the bottom hangs the caisson which encloses the 5th atomic bomb. The caisson swings gently in the current, like a cradle rocked in a subsurface wind. Grim silence has settled over the lagoon. On the Cumberland Sound, automatic controls have taken over. Panel lights flicker. Transmitters hum. Tension grows. Perspiration beads foreheads, though the room is air-conditioned. Time now is measured in seconds.
10, 5, 4, 3, 2, 1, fire!
A flash of yellowish light, and the lagoon erupts as if the earth beneath is disemboweled. Up goes a geyser like 1,000 Niagaras in reverse. 400,000 tons of water rising vertically against the pull of gravity, scattering fragments of the LSM-60 over the lagoon. As it rises, the column cascades outward into a spiked cauliflower. Then collapse begins. At 1 second, the column has reached 4,100 feet. At 60 seconds, 7,600 feet. The crown of the cauliflower curves outward and down, shadowing the target array. This is the derby hat phase. As the column plunges back to the sea, a surge develops at the base of the column, and a wall of spray, foam, and poison fog sweeps outward at the initial rate of 60 knots, an unpredicted phenomenon. This is the most poisonous fog that mankind has known since the dawn of creation. It contains residual plutonium. Whirling and seething, the fog dwarfs and engulfs the vessels, and for a time enshrouds the lagoon. This surge reached a height of 2,000 feet and extended over a radius of 8,000 feet. The rain and mist covered an area of 15 square miles and was lethal over an area of about 9 square miles. Slowly, winds carried the murky cloud to the northwest. For an hour, it was readily observed. At the end of 2 hours, it could no longer be distinguished from the normal cloud mass on the horizon.
Gigantic waves had been created by the explosion. These were 94 feet from trough to crest at 300 yards from 0 point, and 9 feet from trough to crest at 2 miles. The first wave raced out at 45 knots, rocking the entire fleet. Bomb-produced surf was clearly visible to orbiting planes. Although these waves represented less than 1% of the bomb energy, they contributed significant damage to at least 5 of the target ships. Between the base surge and the radioactive rain which fell on the lagoon from the cloud, all but 9 of the target vessels were alive with contamination immediately after the blast. Witnesses searched for adjectives to describe the might of this explosion. They had no precedent with which to compare it. One fact alone stunned the imagination. The blast had produced an 1,100-yard circular crater 25 feet deep in the floor of the lagoon and had flung up over 2 million cubic yards of bottom material. After the blast, there was a layer of mud and sand several feet thick on the bottom of the lagoon in the neighborhood of the detonation point. The condensation cloud gave the blast a momentary appearance of a birthday cake on a platter. This condensation stage lasted but a brief moment. By 4 seconds, the cloud had reached maximum size, roughly 1 mile in diameter. At 18 seconds, it became ring-formed and began to stratify. By 30 seconds, it had vanished. The amount of energy released was normal for a bomb of the Nagasaki type, comparable to the energy released by the explosion of 20,000 tons of TNT. Drone performance was even more satisfactory than on Able Day. All drones and mother planes were jolted as if by a close burst of flak. The B-17, which was flown over the burst at 6,000 feet, was battered by the shock wave, but completed its flight and landed safely. Its bomb bay doors were warped. All inspection plates were blown open. The tail gunner's escape hatch was blown inward. The canvas boot over the tail wheel was split. Study of the flight analyzers revealed that this aircraft underwent reactions never before explored in flight. The air shock wave at 6,000 feet was approximately 1.9 pounds per square inch, lasting more than 1/2 second. Another drone at 16,000 feet was over the target center 2 seconds after detonation. Its cameras, aimed vertically, produced an interesting record of the burst. The air shock wave at this altitude is illustrated by the severe shaking of the aircraft, which stopped the camera. Engine operation of the drones was not noticeably affected. Radio control, even during moments of the blast itself, was not affected at the distances studied. Far less radioactive material was present in the air than after the Able Day explosion. One B-17 drone landing at Eniwetok was slightly damaged when wind conditions and brake trouble caused it to run off the end of the runway and over an embankment to the coral shelf. Damage was not severe, and recovery of instruments with recorded data was complete. Within an hour, the first radio-controlled drone boat was sent into the target array to collect water samples. As the drone boats returned from their sampling missions, crews hosed them repeatedly to wash off radioactive spray. The drone boats were used for radiological surveys for 2 days after detonation. They could go with impunity where man still dared not venture. Meanwhile, salvage crews and instrumentation teams had entered the target array to collect the recording instruments which had been set out. Film from the towers was recovered and rushed to processing laboratories. Boarding teams removed animals from target ships under difficult conditions because of time limits imposed by radioactivity.
As reports filtered back from inspection crews, early estimates of damage were made. The LSM-60 directly over the bomb had completely disappeared. The 26,000-ton Arkansas, moored 200 yards from 0 point, had capsized and sunk within the first minute after the blast. She settled upside down on the floor of the lagoon. Divers found her bottom sieved with holes, her side shell plating broken at many points. Rivets had failed at seams and butts, and her hull was indented as much as 6 feet in some areas. Virtually all her damage was below her waterline, a characteristic of Test Baker. The Saratoga had been 350 yards from 0 point. She had suffered no severe structural distortion or hull ruptures, but she was sinking from progressive flooding through leaking rivet seams. The forward half of her stack lay across her flight deck. The stacks, surviving the blast, were carried away by mass movement of water. Shortly, she developed a slight starboard list. No salvage crew could approach. Radioactive death lurked everywhere. Not even a pelican hook could be attached to her anchor chain to tow her to shallow water. It was the death of a gallant warrior, bleeding oil in great gushes which spread over the lagoon. Her guns now silenced forever. 7 times the Japanese had announced this ship sunk. Difficult now to watch was the death of old Sarah. After 8 hours' struggle, she gave a final lurch, straightening herself for the grave. At 16:16, she slipped beneath the surface, leaving a lonesome gap against the late afternoon sky. The Japanese battleship Nagato had begun to list to starboard and settle by the stern shortly after the explosion. She had been moored at 745 yards and was flooding progressively. By a quirk, one of the mooring buoys of the capsized LCT 1114 had been cast up on her deck by the blast. She was radiologically unsafe to board, and though salvage crews begged to take on the job of damage control or beaching, permission was denied. On the 4th day, when her doom was certain, orders were issued to be prepared to torpedo her next day as a test of new torpedoes. But she spent her last moments alone in the moonless night, unseen. When morning came, she was gone. Air bubbles told where she had sunk. 3 submarines sank in the explosion. The pilot fish went down, nearly all compartments flooded, the tops of her ballast tanks no longer tight, and her superstructure dished in. She had been 260 yards from 0 point. Divers recovered vital instruments that had been attached to her deck and bridge. The skipjack, at 800 yards, went down with a crack in her athwartship plating above one of the torpedo rooms. Later, she was raised and returned to San Francisco for detailed study. Her forward battery compartment and her control room were flooded, and the tops of her ballast tanks leaked. The Apagon, at 845 yards, sank in deeper water, with most of her compartments flooded. Her conning tower hatch and several bulkheads had failed, and a tank top was ruptured. Divers found a hole through the pressure hull forward. A fourth submarine, the Dentuda, submerged at 1,500 yards, had settled to the bottom from flooding that a crew could have controlled. Raised, she had to be beached. Damage to other submarines was not significant, although raising them called for solid seamanship by divers, salvage workers, and deckhands. Exteriors of all the submarines raised required decontamination. Submarine hulls proved their ability to absorb much damage. Nevertheless, submarine batteries, although shock-mounted, proved seriously vulnerable. The concrete barge YO-160 sank immediately. Another small craft, the LCT-1114, was capsized by the burst. Her bottom showed no evidence of damage. Demolition charges were used to sink her. 5 ships were immobilized by the blast. The Fallon, nearest of the APAs to the explosion at 500 yards, had her shell and bottom wrinkled, her decks buckled, her hatches dished in, her boiler foundations stressed, and her air casings ruptured. On the Fallon, as on several other ships, radioactive coral sand from the lagoon bottom and fragments apparently from the LSM-60 were found. Beached with the Fallon was the destroyer Hughes, which had flooded through fractured sea connections and piping. At 635 yards, all her boilers were badly damaged. Her main engines were inoperable. Wave action had damaged topside hamper, and 2 torpedoes hung precariously from her deck tubes. The Gasconade, 580 yards, flooded her engine spaces through broken saltwater lines, but she remained afloat. Her shell was wrinkled, her hatches were dished in, and much electrical equipment was damaged. The cruiser Pensacola, crippled by the air burst, was the largest ship immobilized by the underwater burst. She was 640 yards from 0 point. Her boilers were badly damaged. 3 of her main battery mounts were inoperable. Propelling and auxiliary machinery was seriously damaged. Hull damage added to the destruction. Shell plating was dished in, and bulkheads and stanchions were deranged. She was kept floating only by difficult salvage operations. The LST-133 was rendered immobile by damage to her main deck, hull, and ballast tanks. Flooding made her machinery inoperative. 5 ships suffered serious loss of military efficiency. 3 of these were battleships. The New York, at 820 yards, suffered minor flooding from opened seams in shell plating and tanks. 3 turrets were inoperable from fractured holding down clips. 2 boilers were temporarily useless, and her fire pumping system and a diesel generator were rendered inoperable. The Nevada, at 1,030 yards, suffered damage to her main steering unit and diesel generator. The holding down clips on one main turret were sheared off, making the turret inoperable. Much dished-in plating was observed. The Pennsylvania, at 1,200 yards, suffered minor structural failure and leaked through stern tubes and shaft glands. The Salt Lake City, at 1,200 yards, leaked after the heavy hull shock through stern tubes, shaft glands, rudder bearings, and some piping. The destroyer Mayrant, at 815 yards, received damage to bulkheads, stanchions, and weather hatches, plus flooding from broken lines and some boiler damage. In general, surface vessels within 800 yards were either sunk, rendered immobile, or seriously impaired in military efficiency. Slight loss of military efficiency was felt by vessels as far out as 1,300 yards from blast center. The range of major hull damage for typical service combat vessels was approximately 625 yards. The range of minor hull damage was approximately 950 yards. 8 of the 18 target craft on the beach were swamped or partially flooded. 1 LCVP was washed off the beach and sank. Baker Day, however, produced information more overwhelming than the vast extent of ship damage. For the first time, the insidious potentialities of radioactive contamination were fully revealed. These death-dealing potentialities had been predicted. Now they were actual. Months later, lingering radioactive contamination was an invisible menace to any form of life at Bikini. For days, and in some cases months after the tests, monitors carried out extensive patrols of Bikini Lagoon, the target ships, aircraft, the islands, the air, and the open sea adjacent to the lagoon. Shortage of monitors handicapped the work, but by dint of great effort, it was accomplished. Data from thousands of radiation recording devices had to be tabulated in these studies. For the first time, detailed studies of radioactive contamination could be made. In previous atomic explosions, most of the radioactive poisons had been carried off in the mushroom clouds. Now, about 50% of these fission products remained in the water where they had been discharged by the blast. Decontamination was a grave problem. Methods had to be improvised to reduce the overall contamination sufficiently to allow collection of instruments and technical examinations. The poisons restricted the movement of men and ships. They made target vessels uninhabitable for long periods. They revealed how a harbor or an entire city could be crippled with silent, unseen death. In Test Able, gamma radiation was dominant. In Test Baker, alpha and beta particles were an added danger. Months after the explosion, target vessels were death traps for human life because of these radiations. Continuous monitoring was necessary to protect workers from undue exposure. Fatalities could occur from ingestion or inhaling of microscopic quantities of plutonium or long-lived fission products. The deadliness to humans is aggravated by their tendency to accumulate in the bones. Radiologists knew that alpha radioactivity from plutonium diminishes very little over periods of years. How to cope with this plutonium poisoning is still one of the chief problems of health physics and of industrial hygiene. Decontamination of dangerous areas requires new knowledge and new techniques employed by large groups of skillfully trained radiological personnel. Gamma radiation in Test Baker differed from similar radiation in Test Able. In Test Able, the period of intense gamma radiation was limited to seconds. In Test Baker, intense gamma radiation remained in some areas for weeks and in others for months. Radioactivity in the water was created by fission products which emitted beta and gamma radiation and by unfissioned plutonium from the bomb which emitted alpha particles. The alpha particles themselves are of low penetrating power, but micrograms of alpha-emitting material within the human body are fatal. Gamma rays readily penetrate flesh, water, and clothing, but are reduced to half intensity by about 1 inch of steel. The cloud and base surge caused a radioactive precipitation 1,800 yards upwind from 0 point and 2 to 5 miles downwind. This rain deposited radioactive material on the surface of the water. Six days after detonation, extremely high radioactivity was reported in the layer of mud and sand on the bottom. Diffusion and convection currents had done their work. Radioactivity would have brought death to thousands of men if personnel had been exposed on the target ships. At 1,000 yards, topside personnel would receive fatal doses within 1 minute. If their ships were immobile or contaminated, they would receive 20 times the lethal dose within an hour. These are grim facts. Topside personnel within 1,700 yards upwind and 2,500 yards downwind would receive lethal doses within 5 minutes. If they sought shelter below decks, the dose would be reduced by more than 1/2, but survival would be a long chance only. Porous materials such as cordage, canvas, and wood were much more heavily contaminated than were metal surfaces. Ships with wooden decks absorbed much more radioactive rain than did ships with metal decks. Closed hatches and ventilators kept much radioactive material from penetrating the interiors of target vessels. When leakage did occur, decontamination problems were serious. Certain below-deck areas on the Salt Lake City read as high as 20 Röntgens per 24 hours, 13 days after the blast. Similar below-deck conditions existed on other vessels because radioactive water had entered through openings resulting from Able Day damage. Submarines being submerged were not subjected to the radioactive rain, so contamination was less than with surface vessels. Bitumastic applied to submarine hulls showed a particular affinity for radioactive products. Decontamination of this porous material, when necessary, was difficult. Target vessels were not alone in exposure to radioactivity. Support ships operating in the lagoon began collecting deposits of radioactive material in their evaporators and saltwater lines. Removal of these deposits presented serious problems, and crew activity had to be carefully monitored. Marine growth and rust spots also favored accumulation of fission products. This situation posed a separate problem requiring attention upon return of the ships to major ports. Fewer animals were exposed in Test Baker, but results were even more striking. Virtually all of the Test Baker animals were dead by 1 November 1946, victims in most cases of gamma radiation. No animals were exposed topside. The animals were placed in the sick bay operating rooms on 4 APAs, the Gasconade, the Briscoe, the Catron, and the Bracken. Death of pigs and rats on the Gasconade, Briscoe, and Catron was caused by gamma radiation which passed through the metal of the decks and bulkheads after emanating from contaminated material which surrounded these vessels. When recovered, the more heavily irradiated animals were already in a dying state, capable of only feeble muscular activity. Others suffered from diarrhea and extensive hemorrhage into the skin and other tissues. Although the greatest amount of shock from the Baker blast was transmitted through the water, the shock wave in the air was equivalent to that from an explosion of 4,000 tons of TNT. Through instrumentation, scientists confirmed that the peak pressure in the water at close distances was greater halfway between the surface and the bottom than it was just beneath the surface. The positive pressure in the water, a tremendous hammer blow against the hulls, lasted for about 2 milliseconds. The negative phases and reflected pulses followed. Underwater pressure was irregular because of different angles of reflection from the bottom of the lagoon. As quickly as possible after Baker Day, technical and scientific groups made their inspections, gathered up their test materials, instruments, and data, and returned to the United States. General homeward movement of the task force soon left only skeleton logistic detachments and radiological survey teams behind. By September 26, 1946, Bikini Atoll was completely evacuated. Entry of unauthorized shipping to the lagoon is still restricted. Many of the target ships remained at Kwajalein for further radiological study. All ships of the supporting force were carefully monitored when they arrived at United States ports. Those that showed residual radioactivity were decontaminated. At the Joint Task Force headquarters in Washington, work of preparing the General Joint Task Force report and more detailed unit reports was accomplished. Scientific analysis was initiated at military installations, universities, technological institutes, and research laboratories throughout the country. Obviously, only data which could quickly be extracted and readily be analyzed could be included in the preliminary reports. But even these soon grew into 30,000 pages of technical matter. They are still growing. Complete evaluation and correlation of significant information will require years. Some results had an immediate practical application. Some groups will continue to be interested in dynamic effects of the explosion, the ship, water, and air motions and their consequences, radiation, shock pressures, displacements, stresses, and distortions. Other groups are concerned with measurement of physical change wrought on materials. These changes include transformations in solid structures, loss of strength, metallurgical effects, absorption of radioactivity, and decline of corrosion resistance or durability. During July and August 1947, a year after the Able and Baker explosions, a comprehensive resurvey was made of Bikini Lagoon. Studies were made of residual radiation, particularly in food organisms. Great attention was given to dangers from alpha radiation. New biological specimens were taken both from the islands and from the surrounding reefs and waters. Deep cores were drilled into the coral to determine atomic effects upon reef-building processes. These cores went almost twice as deep as previous drilling in a Pacific atoll. Divers raised important instruments that could not be previously recovered. The sunken Arkansas, Saratoga, Nagato, Pilotfish, Gilliam, and Apagon were of revived interest. Examination was also made of a portion of the LSM-60. Scientists were particularly interested in types of rupture, heat effects, and radioactivity. For the first time, underwater television was put to scientific use. An underwater camera was lowered over the submarine Apagon, lying in about 160 feet of water. While no new data was obtained by this experiment, the test pointed the way to interesting developments.